welcome all the participants once again on the day 4 of this 1 week AICTE Training and Learning Academy Faculty Development Program on 3D Printing Design and Technology. Well, our respected speaker have joined today, and he will be delivering his talk on the topic of powder production and characterization for additive manufacturing. So let me introduce our distinguished speaker of the day. Dr. M. Manjaya is an assistant professor in the Department of Mechanical Engineering at NIT Warangal. He received his MTech with a specialization of Production Engineering System and Technology from University VDT College of Engineering, and his doctorate is from NIT Surathkal in the year of 2015, and he has around 3.5 years experience of postdoc from University of Johannesburg, South Africa, and École Centrale de Nantes, France. Prior to joining NIT Warangal, he has worked as an assistant professor in the Institute Manipal Institute of Technology from 2018 to 2019, and he's an active reviewer of various journals like Elsevier, Springer, Taylor and Francis, Sage, IoT Science, and Emerald. So I warmly welcome Dr. Manjaya, and I request Dr. Manjaya to please start his talk on the relevant topic. Well, sir, now you can share your screen.
Thank
Vishal?
you, sir. Thank you for the nice introduction about me. Now, today I would like to give a brief overview of this powder production, which is very relevant and which is essential for this the additive manufacturing. Is it my slides are visible, sir?
Yes, sir, it's
Yeah.
visible. You
Okay.
are audible.
Yeah. Fine. Thank you, sir. Very good morning to all of you, my dear colleagues and my dear friends. Yeah. In this area, I was working since from 2016 onwards, especially in the IT manufacturing area, and many of kinds of powders we have used, like starting from the aluminum, stainless steel with the different categories of manganese steels, 304, 315, with all the different categories of stainless steel, even with the titanium, inconel, and other the intermetallic materials, and also the different kinds of functional grade powder materials also we have tried. We have done so many testings with how this powder is very much important in this additive manufacturing process, because powder is very much essential and very much important, especially when you use this the additive manufacturing process like the powder bed fusion process or like the direct energy deposition process. The quality of powder is whatever we are using in AM process, it plays a very key role in concerning the process performance and the end part quality and all. If you want to understand very in depth of this the additive manufacturing parts, you should first need to know the powder properties. Whatever you are going to build the part, for that, how the powder quality is there, the powder quality for that part and all, that is very much essential and all. Like that will help us to reduce the powder cost, and it is facilitated by the choice of the powders than the which is offered by the other machine suppliers and all. Means if you first understand the powder properties and qualities and all, then you should know what type of the quality of the part you can able to build and which is required for the particular application and all. Even if you see the whole market, according to the whole market for this powder cost are the second largest cost which is associated with the producing this additive manufacture. This was the major cost involved is in this manufacturing of this additive manufacture parts and all. Like any component we are going to build with this powder bed or maybe direct energy deposition, it consists of thousands of finely spread powder particles and all, which is uniformly laid over on this the powder bed and all. And then when it is interacting with the beam, either the electron or the laser, we are going to have the solidification or sintering, then you're going to have the product. In this overall IT manufacturing market, like there is a exponential growth from last few years, like last from the 5 years. Uh, During this timeline, the sales of these powders and these equipments related to the IT manufacturing is exponentially growing, because the adoption of this process, the IT manufacturing process, especially in the aerospace, oil and gas industries, marine industries, automobile and medical applications, are day to day is growing. Because of that, the requirement or the growth of this the powder production is very much essential, and it is growing a lot in this manufacturing process and all. And whenever you see the need of the industry is very fast, and it is reproducible, and it is very close process to powder characterization techniques is cheaply rising with this increasing application of the AI manufacturing equipments and all. That's the main reason of the growth of this IT manufacturing technology and the powder production and all. Means all this the DD technology or the powder bed technology are the required for this the powders and all. What kind of powders? Means when you see this the US market, like the metal powders market size is like they have some survey they have made, and they are also told that the around the every year we are using around US dollars of 32.6 millions of the powders was sold out for using this additive manufacturing process and all. And we are using earlier, like for powder metallurgy process and all, like pressing, sintering, and even in metal injection molding, uh, that also we are using. But earlier the dominant was this powders are used for this powder metallurgy process in the marketplace. But there is a potential growth in this the metal powders, especially for the IT manufacturing, which is considerably growing very lot in this IT manufacturing process, because of the so many requirement and the need. We need to understand how these powders are produced, and how it is characterized, and what type of powders is very much essential in this IT manufacturing process are required and all. If you see here, whenever how this relationship between this the powder properties and the part qualities, the part property, what property we are expecting in the part, that is the final component, means that is density, and the surface roughness, and the mechanical properties, and as well as the internal build flaws, means that is the build flaws of the component. And also we are having the accuracy. These are all the main properties we are expecting in the part quality and all. These qualities are depends upon the powder properties. Means if you divide this powder properties in multiple levels, like the lowest levels to describe this powder is the physical properties, the physical or chemical properties of the individual powder particles and all. Like and the second level which we are discussing, like the powder properties, how we are describing this powder properties, means like the behavior, how it is behaving, the behavior of the powder ensemble with this like bulk powder behavior and all. That is how this second properties, which is level of the second properties of the powders and all. And a third level to describe this powder properties is like the a behavior of the powder under process specific conditions, means under certain specific condition how this powder is behaving, like in process performance and all. That is the third level of the behavior of this powders and all. Means like the powder properties, the bulk behavior, and as well as in process performance, these are all going to gives their part quality, how the part quality will be there. And the required properties, these are all the properties of the part quality as required, that depends upon these levels of this powder qualities and all. And if you see the powder manufacturing, means how these powders are manufactured, means wherever we requiring these bulk properties or the individual pore particle, chemical and physical properties we are expecting. But to get these the required properties of the powder, what happens whenever we the metal making powders are there, like making the metal powders, the first step in this powder metallurgy is the making of this metal powders and all. There are main four processes which are used for the production of this metal powders and all, like the solid state reduction process, and another one is the whatever I was mentioned here, gas automation or automation process, like plasma automation, plasma routing, electrode process. These things are especially we are most commonly used for this manufacturing of this ready manufacturing powders and all. This process will give us very high quality powder that is suitable for the IT manufacturing process and all. And other kinds of process are like electrolysis process and the chemical processes. These four are used for the production of these powders and all. And if you see the a single powder production method is not only sufficient for all the applications and all, like the powder metallurgy or with the other kinds of processes, it's not applicable for manufacturing process or metal injection molding process. It's not applicable and all. If you see this, there are different kinds of methods of the productions of the powders and all. The mechanical method may be there, the physical method may be there, and also the chemical methods also there. In the mechanical methods, which is the very cheapest way of the production of this powders and all, uh, that is the very cheapest production of this powders and all. And this method involves like the mechanical forces, like by the action of the compression or the shear, by the impact, we're going to make this powders form of a bulk material into a powder form by application of this mechanical forces and all. A mechanical method like ball milling and all, these are all the common examples. The ball milling we are using in this powder metallurgy applications, making of these powders of different alloys or different even with addition of metal matrix, such type of powders also we can able to build with this ball milling process and all. And other types of the process is like whatever I was telling, this oxide reduction methods, there are many methods to produce the powders. Like automation is the generally a very efficient process for making this efficiently highly geometrically precise powders, spherical powders, that only can be achieved with this automation process, like gas automation process or water automation process or the plasma rotating electrode automation, direct reduction process with appropriate gases like the nitrogen or the argon gases we are using, like inert gases we are using for making this powder, because not to oxidize the powder particles. And which are we are also using some water automation process also. We'll study how the can able to categorize different kinds of powders and all. Like you are aware of all this powder manufacturing process, like solid state electrolysis, automation, gas automation, and as well as the other kinds of process like mechanical and chemical process. The and based on this, we are analyzing this powder characteristics and all. You can see the metal powders, how we are analyzing the characteristics. Means the major characteristics are these the flow properties, interparticle forces, the powder droplets, the powder properties, and the flowability properties. Mean the flowability of the powder, how we are defining from the flow properties. The flow properties are mainly from these powder properties, that is the chemical properties, and as well as the interparticle forces. These interparticle forces are mainly affecting the formation of this pipe. Means like in the market we are having n number of the powder manufacturers are there. Those are going to supply for this the powder metallurgy process and as well as for this additive manufacturing process. But we must know that which powders are efficiently suitable for this our SLM process or the DED process. To identify that, we need to know what kind of powders are required for this additive manufacturing process and all. That is especially depends upon the properties of the powder which we are using in this AM process. The properties of these metal powders are mainly vary at that depending on the automation methods and also the other manufacturing conditions and all. And if you see the trend, as I told you, the global trend of this metal additive manufacturing machines opportunities, like this was projected 2019 to 2029. If you see the machines and the materials, the growth of the hardware sales and the material sales is rapidly increasing from the every year, and we are expecting by 29 it is around US 3000 dollars of these materials are expected and market. And also if you see the US, hello,
Yes, sir.
any noise, any problem?
A little bit fluctuation in noise, distortion in noise.
Is it my noise audible right or some disturbance?
Yes, sir. Yes, sir. Your voice is visible, but little distortion.
I think some participants mic is on, sir, like they have to mute.
Okay. Let me see.
Some participants they have switched on the mic. Please switch off your mics. Otherwise, okay. Yeah. When you see this, the market values of this the metal powders and the metal machine opportunities, it was expecting to be increasing in the every year. Like even you can see in the right hand side, it was already the all the IAM materials, that is the powder materials and as well as the metallic AM materials only. If you see this, the rate of growth will be. This is from the Oller's report. The growth is increasing very rapidly, as this researchers have shown that the metal powder cost will be the highest continuous expensive throughout the life of additive manufacturing machines and all. That is the major requirement of this additive manufacturing machines powders and all. The quality and the consistency of this EM components depends in part, and also the characteristics of these powders starting from the powder feedstock and all. Means how we are feeding the powder in the AM process, like whether it is in with and the nozzle we are feeding the powder, or with the conical axial, or with the in the powder bed spreading over the powder on the bed and all. That is means we have to understand the controlling and understanding the quality of powder both in as supplied or in the reused conditions also is essential, because in additive manufacturing process, whatever we are using powder, around 40 to 60% of powders only are used for this additive manufacturing process. Remaining around 40% of powders are not used during the process, means which are to be reused by the automation process or receiving and sorting of this partially melted or melted powder particles, like unmelted particles will be there. That's why we have to receive and reuse that powder for the same process and all that. How we have to reuse that, we have to analyze that, we have to check how can we able to reuse and all. And means if you beginners of this additive manufacturing technology, you are going to decide which powders are required for this our additive manufacturing process and all. Whenever you are deciding the which powder suppliers we need to use, like all the powder metallurgy powders cannot be used for this additive manufacturing process and all. Like we need to have additive manufacturing equipment suppliers. Like you might have known that the EOS, Praxair, the Oganas are the very well validated powder suppliers in the market and all. Means these are all validated powders which are used in this additive manufacturing process and also very much suitable for this AM process and all. Well, the validated powder can be a de-risk for producing the powders for AM process. It does not limit that users to a single source supplier and inhibits the development of in-house expertise also. It means based on this, whatever the data as was expected, that is 2013, there are around 855 powder manufacturers in the worldwide who are capable to produce this. The powders of estimated 1.12 millions of the metric tons per year they can able to manufacture the products which is cost around the US dollars of 6.9 billion and all. Means we are having so much many number of the powder manufacturers are there, but we must know what kind of powders we are going to use for AM process and which suppliers we have to choose. Nowadays there are many manufacturers are there, not only from the Praxair, Oganas. These are all the most widely validated suppliers of these powders and all. Compared to that, there are others also there in the recently, many manufacturers, even in well are there, and thermal spray technique, and those suppliers also thermal private limited, and these are all the suppliers. 3D systems also making this. Indomim also making the metal powders and all. But the must know the what kind of powder, what is the requirement for our machines like SLM process or for the DED machines and all. Means if you see the selection of AM powders, on what basis we have to select this AM powders and all. Means first is the importance of the powder, routes of powder production, and powder recycling. These are all the main requirement when you are selecting this additive manufacturing powders and all. Like the importance of the powder means AM process uses these powders as a raw material. Like a feedstock will be having the critical influence of this final quality of the powders. And that means when we are feeding in the DED process, it is coming through the nozzle by the hopper and all, through the organ gas as a carrier gases or the nitrogen as a carrier gases, inert gases, take from the hopper to the nozzle head and all. Means during this flowability is very much important in DED process of this powders and all. And even in SLM process, what quality of powder we are using means the quality of powders plays very much essential in SLM process and all, because there is a contains a discrete amount of the powders which is contained in the hopper, and it's going to spread across the build chamber, whatever the build plate or build chamber, in the thin form. Means how much layer thickness we are defining. Based on that layer thickness, the roller or the blade, doctor's blade, is going to take the powder and spreading over the build chamber and all. Means what happens, it is when it is spreading over the entire the build chamber area or the build plate, if consisting of this homogeneous powder, then the entire build chamber area will be of uniform layer thickness. Means what happens, if there is an inhomogeneity in the powder, then it's going to resulting in the porosity formation or incomplete thickness melting of the layer is going to be taking place, because the powder, the particle sizes are not homogeneous. Then you are going to have the inhomogeneity in the powder particles. It's going to create too much powder pull upon one particular area, going to be incomplete melting during the laser or the electron beam interaction. That is the main importance of the powder we have to choose for a DD process or for the SLM process. You can see you are aware that the what is the size range we are using. Means 5 to 45 micron we are using for this SLM process, and 45 to 90 or even 110 some machines we are using for this DED process and all. Even in the biojet process and all, we are using around less than 25 microns of powder particle sizes we are using. There are a requirement of these powder particle sizes, especially the metal powders. And even in SLS and mindset, we are using some polymer powders and ceramic powders. That is, we are using around in the range of in the SLS 20 to 80 micron we are using, and in mindset we are using around less than 25 of polymer powders. Also, we can able to use that and all. And you can see the spread of powder in this SLM process selectively fused using either a laser interaction or the electron beam interaction that is inputted by this 3D CAD model, that is slice 3D CAD model. The layer is spreaded. The hopper dosing and bulk packing performance of the AM powder depends entirely on the properties of the powder which is being used in the spreading of the build platform area. The actual component build volume is significantly less than the total volume of the powder that has been spread. Means, as the consequences, there is a large amount of unused powder left over the build chamber in the SLM process or SLS process. For the given high cost of the metal powders, it is essential that the unused powder is effectively recovered and reused in future builds and all, because we need to know how recovery we have to do in the entire chamber and receive it and reuse for the same process and all. That is effectively we have to recover the unused powder and all. Like, however, the effect of this continued recycling of the powder, unused powder and all, the actual powder properties, that is the original powder properties, and this received or reused powder properties have the slight difference will be there, that we need to understand that how it is affecting the quality of the powder handle. Means, and also there is a ratio which we are using the reduced powder with the original powder handle. Means maximum of we can put around 30% of the reused powder in the original powder when you are using for this additive manufacturing the part and all. Means, and you should understand what are all the roots of powder production, how these powders are produced. If you see here the roots of powder production, like from the ore we are extracting, and then we are making the powders and all by the extraction of the hydrogenation or dehydrogenation, and then forming, and then we are making with the billets or wires with the wire drawing technologies and all, and then we are using that type of the ingots. The billets are in the form of a wire we are using for the automation process, or it may be the different kinds of automation, plasma prep, RF, or with centrifugal automation. We are using such kind of ingot to make the powder, and then after that post processing of that powders we are doing, and then validation of that powders is very much essential. This is how the roots of this powder production is generally we are following this making of these powders and all. And as I was discussing, there are different kinds of powders and all. Means, we'll see how in-depth the powder production is taking place with the different kinds of process and all. If you see here, the automation process, like automation is going to majorly using in the additive manufacturing process, automations of the powders and all, and what kind of microstructure we are expecting also very much important in these processes. If you see here the automation, it is going to break up the liquid metal into a fine droplets, typically less than this 150 micron. Means this breaking of this powder particles, the liquid metal into a fine droplets by the force of this molten metal through a small orifice and breaking through the stream of powerful gases of a compressed air, or like water we are using to make this small fine droplet powder particles and all. This is how we are general procedure of this the automation process. It means in the automation means any material that can be melted and can be made into droplets by this disintegration of this liquid and all. Means the automation process is a independent process which is going to be normally a physical and mechanical properties which are associated with during this solidification of the molten material and all. Means, this method is widely adopted in IT manufacturing process making of these powders and all, especially for making very high pure metals and as well as the pre-alloyed powders that are directly from the ingot we are going to melt and we are going to make these powders and all. Because whenever you are using these powders in AM process, we are having a lot of different quality of powders are there. That comparison also we'll see how different process we are going to get different kinds of powder properties, powder characteristics and all that we'll discuss, because this will mainly affect the feed quality of the powders and all in this DD and SMM process and all. Because if you see the based on these categories, as I told you, the automation media like gas and water, and under the energy sources, kinds of energy, centrifugal, vacuum, plasma, ultrasonic automation, and all. And what is the mechanism of this automation? How this the mechanism is going to be taking place in this automation process of whether it is a water automation process or it may be the gas automation process, means uh, that depends upon the quality of powder. Means in this we need to understand the how mechanism is taking place during the automation process. And you can see the four stages are there in the automation of this metal powders and all in the gas automation or in the water automation process. Because there is a entrapment of inert gases during this process that also going to be entrapped in the powder particles, and that makes porosity inside the powder particles also. That's why that is the powder induced porosity and all that going to be happen the during solidification and all that also creates the effect in the fabricated part quality and all. That's why we need to avoid that pores in the powders itself. That is how we can able to control efficiently the production of these powders and all. That's why it is very much essential to understand this mechanism of this powders and all. The mechanism of these powders, if you see here, the in the stage one, as I told you, the four categories are four stages are there. In the first step, the impingement of high velocity of jet of water or the gas produces the a sinus wave. Means what happens, it is going to create the a sinus wave in the molten metal, in the molten core, which causes the disturbance in the liquid sheet. Whatever that liquid sheet is there, if you see here, this is the liquid sheet. It is going to create the sinus wave in the first stage, that is the growth of wave on the liquid sheet. And in the second stage, the wave fragments and ligaments formation through the shearing forces which is produced by the disturbance that is at the first stage and all. Because of the impingement of I force is the induce of this turbulence in the melt that is going to create this the disturbance in the stage one and formation of fragments and ligaments through this shearing forces and all. And in the third stage, what happens, it is going to the breakdown of these ligaments. Means whatever that the ligaments are, the fragments are formed in the second stage, that is breaking down in the third stage, and it is making into a droplet forms and all. That is the primary automation is going to be taking place in the third stage. And the regular particle shape like high surface tension and low cooling rate, and irregular particle shape means it is having the low surface tension and high cooling rate will be there. And in the fourth stage, the further deformation and thinning of droplets and wave fragments into a smaller particles occurs in the secondary automation process. That is in the fourth stage, the secondary automation is going to be taking place. With this the size reduction, which is limited by the melting viscosity, temperature and acceleration forces and all. Means how much force we are creating, and also the viscosity of the molten metal and the temperature of that molten metal, that is what material we are using. Based on that, we are going to have the size reduction control, which is limited by these things and all. If you see here, this is how this the sinus wave is creating in the first stage. because of the high impingement of the force of air or by the water, and then the fragments and ligaments are formed in the second stage, and then in the third stage this is the breakdown of the ligaments into a fine droplets, and then in the fourth stage making of this boards. And means what happens when the water drops hit the are forcefully hit onto the melt stream, it explosive stream packing is going to be taking place. Then it's take away that molten metal into along with that the powder of the metal stream, and the water droplet travel in the same direction whatever the velocity of this water normally of the liquid metal stream, that rather than the velocity of component parallel to the liquid molten stream. And it's going to create this controlling of this formation of the size of the particles, and all that size of the particle diameter is depend upon the impingement of this velocity of this the gas or the water stream on this. The particle shapes, which is atomized by this powders, can be modified from the almost perfectly spherical to a highly irregular, and means by controlling this process, which we can able to interval difference between this integration of the liquid metal stream and the solidification droplets. By this, we can able to control the particle shapes, that is the spherical sphericity of this metal powder, which is very much favored by this the high metal surface tension. Means the sphericity is mainly by the high spherical, like surface tension of the molten metal, and narrow melting range of the powder particles, and the high pouring temperature of the that molten metal, and especially the gas automation, inert gas, gas type of inert gas, and what is the low jetting velocity, the jetting velocity, all these, and the apex angle, means when your formation is taking place, you can see here in the water automation and the gas automation process, the jetting angle, this alpha is the jetting angle. That jetting angle is also very much important, and the flight path, the longer flight path or the shorter flight path, that is also affects this powder quality, the shapes and sphericity and all. And when the particle sizes are formed in this water automation or in the gas automation, we can able to determine that the diameter of the mean diameter of the particles based on this the constant with respect to the velocity of the impingement of the gas or the water with respect to the this impingement, the angle, the jet angle, that is the with respect to sine alpha, we can able to calculate the mean diameter of the powder particles. You can see the water automation process. All this water automation process began with the melting of the feedstock alloy, and this melting process has a number of variations, but generally when automation using water, the feedstock is first melted in the furnace, as if you see in the right hand side, the feedstock is melted in this furnace, and then it is transferred to this crucible that regulates the flow control of this molten pool and all in the automation chamber. Then the liquid is entering into the automation chamber from the furnace. It's a free fall through the chamber, and then with the high velocity of water jet symmetrically positions around this the molten stream and all of a liquid molten stream, and then automation and solidification of particles is going to be taking place in this water automation process. Similarly, if you see here in the gas automation process, gas automation process is the mimic of this water automation process, but only thing is, instead of water being used here, the gas is going to be used as a process for impingement and all in the nozzles. If you see this, the air can be used as an automation process, but what happens, the oxidation is more going to be taking place in especially the highly oxidizing materials and all. To reduce the risk of this oxidation, we are using nitrogen or the argon, inert gases we are using to reduce the oxidation and contamination of the metal. You can see this is how this the powder particles are going to be taking place in the gas automation process, and the ligament sheets are formed, and the third step, the breakdown of that ligaments into ellipsoid or the spheres, and then it's going to make the powders. This is going to be, this is the automation chamber, and it's the collected in this bottom of this chamber and all. And this is the production of this powders and all. And whatever we are using to melting, that vacuum melting furnaces we are using, and stream of liquid is atomized by high pressure jet of gases. Due to low capacity of the gases, the metal droplets have increased solidification time, resulting into a comparatively more spherical powder particles compared to the water automation process. Because in this gas automation we are having more sphericity compared to the water automation process, and also there is no satellites on the spherical powder particles, because the solidification rate is more in this gas automation compared to the water automation process, and we are having increased in the solidification time and all. And worldwide annually we are making of this gas automation to produce the powder, which is around 50,000 tons per year of this gas automation powders are manufactured for the non-ferrous alloys and all, and 300,000 tons of water automations. With even with the air automation, we are making the 300,000 tons per year of this gas automation process for making the ferrous powder particles and non-ferrous powder particles and all. And the melt size and the melt feed rate, which is less than 120 kg per minute, we are feeding the molten pool in the water automation process, and in the gas automation process, which is less than the water automation process. And during this mechanism of this automation process, in the droplet formation, how this droplet formation is going to be taking place, how do we control, how do we evaluate this the diameter of these droplets or the diameter of the powder particles is very much essential. Like in the initiation of this sinus waves rapidly increases in amplitude, that a detachment of the bulk liquid from the molten pool while creating the sinus wave producing the ligament, that dimensions which is depends upon the wavelength of distribution and all. Like the breakup of this ligament into a spherical droplets, like where A is the geometrical constant. If you see the volume of this, which is equal to A into square root of 2g p1 minus p2 divided by rho, means here the injection pressure and the pressure of the atomized gas, and as well as pressure of the atomized like liquid metal, and g is the gravity due to acceleration due to gravity, and rho is the density of the liquid metal and all. Based on this, you can able to calculate the velocity of this one and all, impingement and all. And then W is the Weber number for the metal stream, and dl is the diameter of the liquid metal stream, and dm is the mean diameter of the particles is diameter, and all nl ng are the kinematic viscosity of liquid metal gases and the viscosity of the liquid metal gases, and fl and fg are the flow rates of the liquid and gas. Based on that, you can able to calculate the diameter of the mean diameter of the powder particles and all. In this, we know that how mechanism is taking place and how this powder ligament and powder formation is taking place and all. But during this, whatever the solidification is taking place, that solidification is going to create this the evolution of this microstructure. Means you are aware that like casting or the extrusion process or any other solidification process and all. In the casting process, how this solidification is taking place, and from outside the metal mold or the sand mold, which is like using in the casting process. Similarly, in automation process, each particle might be considered as a freestand micro ingots. When the metal is pouring into the mold, cast mold, to start to solidify from the outer wall to the inner wall. The similar fashion here also, the each particles might have the considered as a freestanding micro ingots. when each particle's droplets are coming out from this molten pool, that quickly solidifies the outer surface to the inner surface. What happens here? The nuclei, micronuclei, the minute nuclei is going to formation is taking place, and the seed crystals are formed in the first. Then during this cooling of this nuclei grow more rapidly along the certain crystallographic directions. Then it is going to form the branches in all the directions. Like branches are called the dendrites, and even small amount of the solute elements in the melt, either as an intentional alloying or as an impurity, greatly affect this solidification process. And that means the process of solidification is occurred by this mechanism of this nucleation and as well as the growth of this crystals. And all means what happens during this the freezing, the nuclei grow more rapidly and along with certain crystallographic directions, and as well as the high result formation of these long branches like structures and all, those are all the dendrites and all going to be formed in this uh, um, during this, the solute atoms tends to remain in the liquid rather than the solidify with the solvent atoms at the crystal liquid interface and all. And as the solute rejected by this crystal becomes the concentrated in the remaining liquid, as a resulting of which is going to be happen like freezing point for the liquid decreases. Freezing point of the liquid is going to be decreases, means when the solute atoms are rejected by this crystal, this is what happening is going to be taking place on that. And when the liquid is just ahead of freezing, the solid liquid interface is more enriched by the liquid further away by means of a composition of the liquid varies with the distance from the interface and all. Means the degree of cooling rate helps by evaluating the relative efficiency of the different cooling techniques for powder production. Magnitude of this cooling rate and its variations in help interpreting with the microstructure of the particles. It is highly highlighted that under equilibrium conditions, many solid alloys solidify dendritic fashions. And that means whenever the solidification is taking place, the it reveals by these dendritic fashions. Means that relationships can be identified, can be developed based on this the cooling rate and the dendritic corner spacing, which is lambda is equal to k to the power of n. K and t are the constant for the given material. Based on that, the lay like the dendritic corner spacing with the help of this cooling rate, we can able to identify what kind of the microstructure we are going to expect in this solidification automation of this materials and all. Means in case of the in whatever we are making the powder particles and all, like what kind of powders are making the microstructure is going to be revealed. This also the in the powder metallurgy process, which is revealed by this microstructure phases which are present in this powder particles and all. And in case of metals and single phases, only one phase is seen. In case of other alloys, gives a lot of information related to the phase which are present, and as well as the relative amount as well as the distribution of the powder particles. And all this depends upon the powder production, alloy composition, and as well as the thermalicity of the powders. Based on that, the total microstructure of the part which is fabricated by manufacturing or by the powder metallurgy depends upon these things and all. And if you see here the comparison of, as I was discussing, the different powders with gas automation, water automation, you can see in the left hand side, these are all the powders which are manufactured with water automation with different magnifications. We can able to see at lower magnification, at higher magnification, as well as at higher magnification. You can see these powder particles are spherical, but it consists of some satellites. Even you can see in the higher magnification at 500x, you can see there are so much of agglomerated and irregular powder particles are also present in this water atomized powder particles. These are all the water atomized powder particles. Means gas atomized powder particles were very regular. very spherical will be there. And if you see the microstructure of that individual powder particles, means as I told you, once the nuclei is created and solidification is taking place, then it is creating the multiple crystallographic growth direction and the creating the branches like tree-like branch structures, and is making this dendritic structure of this powder. You can see this is how the individual powder particle microstructure is going to be taking place. And if you see here the variations in the solidification rate, and which is going to give us the different dendritic RN spacing and all. You can see with respect to different materials, merging steel, aluminum, or stainless steel, or copper alloys, we are having a different solidification rates, and we are going to have the different dendritic RN spacing we are going to get in this solidified powder materials in the automation process and all. And this plasma automation process, which is similar to the same kind of gas automation process or water automation process. Instead of that gas, we are using here for plasma automation is a highly spherical powder production. Instead of the molten pool, we are supplying a wire spool. That spool of wire is the powder is fed directly into the automation chamber, where we are having a simultaneous plasma torch is going to be melt and atomized by coaxial plasma torch and gas jets and all. And if the powder is provided long flight path, the spherical shaped powders are going to be result. Means we are going to have highly spherical in this plasma rotating electrode or plasma automation process and all. We are going to have like highly spherical powder particles are going to get in these kinds of process and all. And the hydride and dehydrate process also there. The hydride and dehydrate process is another kind of the manufacturing of the powders. The hydride and dehydrate methods of powder production differs from this automation process. It does not involve melting of the metal feedstock. It involves like a crushing and milling, and it's like a mechanical process. We'll be having a large lump of materials that feedstock into a fine powder particles and all. And now very recently a triotium process is there. That a process is like relatively a new method which is developed by production of, especially for pure titanium powders, such as developed by this CSIRO Australia. And this tyro process is two stages. It's a continuous production of method in which the titanium tetrachloride is the first thermally reduced into a magnesium chloride titanium composite under the presence of magnesium in a fluidized bed reactor. And then the magnesium chloride titanium composites then separated using the vacuum distillation process, producing the high purity of titanium powder. As it is processed of the titanium powder is unsuitable for this IT manufacturing process. The particle size range is 150 to 600 microns. Means the particle range is more in this kind of process and all. That's why it is unsuitable for this, which is using for the IT manufacturing process and all. And it is necessary that the powder is most modified using these kinds of the trial process. Again, further the shear milling processes, controlling of researching of such type of powders, which can be suitable for IT manufacturing process and all. And if you see the summary of this powder characteristics manufactured by the different process and all, like what kind of powders we are manufacturing with a different automation process. You can see, as I told you, different automation, water automation, gas automation, plasma rotating electrode automation, hydride and dehydrate process, tire process. You can see the range of powder particles we can able to manufacture with water automation is 0 to 500 micron, even in gas automation 0 to 500. And the advantage of this water automation is high output range of powder particles, requires only a feedstock ingot form, and there is a requirement of post-processing in the water automation process, which is commonly a non-reactive powder particles and all. And there will be a irregular powder particle morphology will be there, and the satellite which is present on this powder particles. And the particle size distribution is very wide in this case of water automation process. You can see 20 to 150 the powder particle sizes will be there. And in this, the gas automation, wide range of alloys can be made with this water automation process, and also which is only suitable for reactive alloys. And especially you can see this nickel, cobalt, ferrous, titanium, and aluminum. You can able to use these kinds of, and it can be used as a feedstock in that form, and also we can able to produce very high range of different sizes of the powder particles with gas automation process. And the processed powder particles are very spherical powder particles. There might be a very less satellites may be present, and it's a low powder between 20 to 150 microns and that. And with the plasma automation process, we can have the size range of 0 to 200 micron. Even with the plasma coating, we can have the 0 to 100. And in this process, we are going to get very highly, extremely spherical powder particles in this plasma automation and plasma optic electrode automation process. And here it requires the feedstock in the form of a wire form or in the powder form. And the production rate is in this process is very low, and it's a high cost, and which is especially used for titanium. Most common titanium 364 we are going to use for making of plasma automation process, plasma electrode automation process for titanium powders. Centrifugal automation can be used to make the powders in the range of 0 to 600 micron. We are having a wide range of particle sizes, the particle size distribution. The difficult to make extremely fine powders unless very high speed can be achieved. Means if you go with a high speed, then only you can able to make the fine powder particles. Otherwise, you will be having a larger powder particles, because this is the centrifugal spinning of this molten metal along the centrifuge to make these powder particles. Especially for the zinc of alkaline batteries and titanium and steel shots made with this type of centrifugal automation process. Hydration and dehydration process is range of 45 to 500. It's a low cost process, and we can able to make irregular powder particles morphology with, consisting of the hydrogen and oxygen. Means this dehydration, hydration, and which is very much limited for this titanium 64, and as well as for the brittle hydrates, because initially we are making into hydrates and then making into dehydration and to make the powder particles. And the key process variables, what are all the morphological structures, characteristics we are going to evaluate is the basic properties, the basic characteristics which is used for this orders analysis and all. Means how the determination of this basic properties of this metal powders. Like one is the shape of the morphology of the powder, the particle size and particle size distribution, porosity, and as well as the uh, porosities, microstructure. All these things we are going to evaluate like by this process of characterization process and all. Particle shape, the morphology, how do we evaluate the particle shape or morphology? With the optical microscope or with the scanning electron microscope, we can able to see the morphology of the powder. And how do we evaluate the powder property? That is by the apparent density or by the tab density. Means with the help of this alphameter or Freeman FD4 tab density register, we can able to assess the apparent density and tab density of the powders. The particle size and size distribution only can be done with this sieving method. That is the most popular and the simplest method for particle size testing and all. That is the categorized, means the particle size distribution can be done with this sieving method and all. Even with the laser diffraction, optical microscopy can be done with this particle size distribution, particle size analysis and all. But the sorting out and categorizing these particle sizes in this process is difficult. That's why the sieving is the the most popular and the simplest method. Based on that, you can see how flowability of the powder. Once it is sieved, you can see the flowability of the powder. That flowability can be analyzed by these type of the assessment techniques: Hall flow meter, dynamic flow testing, the revolution example like revolution, Freeman, FD4, shear cell, and angle of response can evaluate with the flowability. That means once it is particle size distribution is done, then you can see this flowability and cohesiveness of the powder particles. The particle porosity, particles porosity can be analyzed only by the polishing of this powder particle. Means that is metallurgical analysis done of the powder particle. That is, particles are immersed in this mounting clay, and then with these glass resins and all, and then it is polished mechanically, and then it is evaluated. And that is the surface area of the powder particles, chemical composition, all these things can be analyzed with the assessment techniques like BT surface area analysis techniques, ICP technique, XRD technique, inert gas vision, combustion infrared detection techniques also can be used to see the surface area and chemical composition. And the particle morphology we are telling, the morphology means that is the surface structure of the powder particles. That's significantly influenced by the bulk packing and flow properties of the powder batch. Whether the spherical powder particles or irregular powder particles or regular powder particles, and the equiaxial powder particles are likely to arrange and pack more effectively than the irregular particles, because the morphology can have a significant influence on this powder bed packing density. Means when you are using in SLS or SLM process, we need to have the highly spherical powder particles, because that depends upon this packing density. Packing density, if you want to have highest packing density, you need to have the highly equiaxial particles, highly regular particles, and it consequently affect the final component density, where the more irregular particles are there. If you are having more irregular particles, then the morphology of the final particles and the density of the final part will be the less, because of the irregularity of the powder particles. As consequences, if you have highly spherical particles, tend to be favor for additive manufacturing process. And this means that the limits in the use of potentially cheaper powder production routes, such as like water automation and the hydration and dehydration, that are not efficiently have the uniform distribution or equiaxial powder particles and all. If you see the different morphology of the powders, you can see hydration and dehydration process, gas automation process, plasma automation, or plasma rotating electrode automation process. This is one of the examples of this titanium powder. If you see here, we are having highly spherical powder particles in plasma automation, gas automation, plasma rotating electrode. But in the hydration and dehydration, it's not spherical, it's irregular powder particles and all. But what happens in gas automation and plasma automation, there is chances of formation of small satellites, and also the wide range of distribution of the powder particle sizes and all. But in plasma routing electrode automation, we are going to have a uniform spherical powder particles of a uniform low volume powder size distribution will be there in the plasma routing electrode. And if you analyze this, what I was told you, how to analyze this microstructure of individual powder particles, whether the porosity or the surface morphology, what we are doing, we are embedding that powder particles in an epoxy, done with the standard metallographic preparation process by hand or mechanical polishing. We are doing polishing and then etching to reveal the microstructure, and then revealing the porosities and in the powders and all. Like if you see the powder preparation for the SEM microscope and all, some powder particles we are coated with electroplating with nickel and all, or tin powder particles and all. Then we are doing the electropolishing with the second electron and with the backscattered electron. How you can see the morphology or microstructure of the powder particles, you can able to see here. And also if you see for the titanium powder, it's coated with a nickel electroplating to improve the particle surface smoother than the after mechanical polishing, and you can see the surface is highly smooth, and also you can see reveal the microstructure of the inside of the powder particles and all. And if you see the with improved nickel coating and all, you can able to see whether the porosity inside the powders and all. You can see these are all the powders are already having some porosities. Means you can see how the surface roughness of these powder particles. That is how we can able to analyze with this nickel electroplating, and then metallographic polishing can able to see these kinds of the characteristics of the powders and how this the powder shape and shape factor is related to this the additive manufacturing process. Like it is majorly influenced by the characteristics of the powder, the ratio of aspect ratio, and the shape factor. The shape factor is also called the shape index. It is a measure of the ratio of the surface area to its volume and the aspect ratio is the ratio of the largest dimension to the smallest dimension of the powder particles. And this volume of the powder is normalized by the spherical particles of an equivalent volume and this ratio ranges from like unity to 10, like spherical unity to 10 flake like needle like structures and all. The shape factor is a flake is higher than the its sphere and all. And if you see this particle size distribution and other properties and all, the particle sizes and all like powder sampling we are doing with the sieving method, and with the sampling methods we are analyzing and all of a metal powder's shape, size, microstructure and all. And the particle size distribution means the size is very much important because it affects the process characteristics of the powders and all. Flow properties of the powder and the compressibility and density are other properties that have an effect on the metal powder behavior. That's why the key role is the flowability properties. That's why in powder flowability has a very much required property of the powder particles for the high powder, bulk powder properties and all. It's not only a compressiveness of the powders of the bulk powder properties. Flowability is an umbrella term which is described for this complex behavior of the powders. That is the major requirement of the flowability of the powder particles. That we are measuring with the principle of a dynamic avalanche angle measurement with the revolution of the powder in the chamber. With the help of the camera, we are analyzing this that flow properties of the powder particles and all. And with the bulk characteristics and the powder characteristics, which is affected by the flow, and that principle can be measured with the flow meters and all. That influences the flow properties and the interaction between this small powder particle units and the large powder particles units and all. It's all the independent of the equipment whichever we are using to determine the flowability of the powder particles and all. And which, with the help of this ASTM standard ASTM D7481, we are using this the Hanna's ratio. That is the straightforward method. Even with the B213 standard, that is the alpha meter standard, that is and the Carney flow with the B964 standard, where numerous standards are used to measure the flowability properties. And if you see when the metal powders are compressed, that is the compressibility of the powder, density, that is the theoretical density, apparent density, and the density of the powder, which is shaken or tapped into the die cavity and all. And these are all the characteristics. In general, EBM can be used to particles, nominal particle sizes of 45 to 106 micron. And for the SLM process, particle size distribution should be 15 to 45. So in some machines, we are using 5 to 45 micron also. And this particle size distribution are very much important. Depends on this layer thickness that potentially lead to in situ segregation due to the mechanically recoater pushing the porous particles away from the bed during the spreading of the powder entire in the build chamber or build platform area. And the build quality is very much affected by this segregation of this sense of these powder particles. Using these powders with a wide range of particle size distribution, high fine content produced with a component with a higher fractional density and all. Use of fine material increases the risk of health and as well as safety issues of the operator. And this is particularly true when processing with reactive materials, as the titanium, where it finds finer particles, particulates are like to be the more flammable and explosive and all. Particle size, shape, and distribution. The particle shape is usually described in terms of aspect ratio. Aspect ratio is the largest dimensions of the particle to the smallest dimensions of the particle. The ratio from unity to 10, that is the 10 flake like needle-like structure, and shape factor is the measure of the shape index of the ratio of the surface area of the particle to its volume. And size distribution is an important factor to consideration because it affects the processing characteristics of the powder center. The distribution of these powder particles is given in terms of the frequency distribution plot. The maximum is called the mode size. You can see the frequency distribution curves, the particle size distribution. You can see we are in the histogram or with the bell curve, we are defining the frequency distribution. Means whenever you are procuring the powder, you might have seen they are given this information, the frequency distribution, particle size distribution, and as well as the chemical composition, and D10, D50, D90, the particle size diameter with the how much percentage of the D10, how much percentage of D50, and how much percentage of D10, D90. All this particle size distribution, they are given in the powder analysis, powder characteristics of the when you are buying the powders and all. Means there are several classes based on this quantitative proportions of the particles belonging to a specific size parameters, and can be described in a cumulative or frequency distribution manner. Like particle size distribution can be determined using various methods to the degree of dispersions and all. Like if it is greater than 50 micron, we are calling it as a porous size particles that used for the sieving analysis to separate out or sort it out. Fine grained powder particles with the microscopic sedimentation, air suppression, or laser particle size analyzer used to sort it out. You can see the powder particle size distributions and all. Even with the image processing, with the image analysis also, we can make use of with the image or with any other MyPar, with the different kinds of softwares are available. With that, you can able to analyze. Once we have the images of the morphology of the powder particles, with the image analysis, we can able to identify the particle distributions and all, particle size factor with the particle distributions and all. And we have done analysis also with the AICTE instruments. And you can see this particle size numbers, particle size fractions also with the cam sizer. Also, we can able to explore this. And the other kinds of powder analysis is like what are the chemical compositions. Means some kinds of recycled powder, means of the powders are partially melted, reused, and we need to analyze before using that unmelted powder particles, because we must know that what is the content, what is the other oxidation effects in that powder. You can see virgin powder is going to give us the what chemical composition existing under powder particles, and if it is partially used powders and then received it, it contains some oxide layer on the particle surface. You can see in this, it contains some oxide layer in the particles. This red, orange color is pink color, is pink color, and as well as yellow color with different chemical distributions and of the elemental diffraction analysis. And if you see such type of powders, if you use the recycled powders, what happens? The one is particle 1 and another is particle 2. This is recycled powder and this is the virgin powder. You see in the recycled powder, we maybe have a chance of getting this the porosities and this lack of fusions and the part component. And that is all depends on the what kind of quality of powder we are using. And if you see this, some researchers have done with same 3D systems machine with the 17.4 pH steels with the recycled powder. After using that recycled powder, what is the microstructure and defects were analyzed with the different powders. You can see here the cross section of this part which is fabricated. You can see this there is a unmelted partially particles which are occurred in the fusion zones of this the successive layers in the multiple boundaries across this epitaxial multiple boundaries and all. You can see if you exaggerately analyze those things with the TM analysis, in the multiple boundaries we are having oxide layers. It is in the beam scan direction. In between that layer fusion, we are having oxide layers because the each powder particles once it is exposed to the machine, it may have the oxide layers. If you are not considering such type of the oxide layer, you are going to have these oxide layers in the successive interface layers of the fusion layers and all. And the elemental mapping also they have done, and you can see this the oxidation inclusions are occurred in some inside cases of this the way the ferrous and nickel copper rich precipitates are formed. There is a oxide inclusions are existing in the materials and all. You can see these are all the large inclusions in the build direction and all. And if you see this small inclusions where the layer of this successive interface between this one layer to another layer, these kinds of the fusions or defects will be there in the fabricated with the part and all when you use recycled powders. And other characteristics, the powder characteristics is required is the cohesive strength. The cohesive strength means like many metal powders like flow like a liquid, such as metal having no cohesive strength. However, when squeezed in the palm of one hand, the material may gain more enough strength to retain its shape once hand is open, once you are opening your hand. If the powder gain are under cohesive strength because of the pressure applied to it, an arc or the rattle can form in the flowability of this powder center. That is going to analyze this cohesive strength of the powder center. A rattle is a stable pipe or a vertical cavity that empties out of the ore powder in the outlet. That material is left out stranded in the stagnant zones that usually remains in place until the external forces is applied to the dislodgement. You can see these two kinds of this rattle formation. One is to identify this the cohesive strength of the pores and all. It is the formation of these kinds and the rattle formation and all. You can see here we have done that analysis. You can see the pore flowability is very good and there is no formation of rattle on that. That is, in this case, we are having this is how the flowability of powder is going to take place. It means the arc formation at the outlet of the bin, and it is going to form. And you can this is how the arc formation is going to be taking place. You can see. And if you see here the rattle formation, the powder is not flowing properly. What happens? This is the outflow meter with B213 stand we are using. the powder is not flowing properly, we are tapping, means we are putting some pressure onto the powder to flow it properly. You can see the formation of this is the rattle. This is going to give us the cohesive strength of the powder particles. Even though this is all the gas atomized powder, we are having different kinds of powders properties. We are going to get it. This is how we can able to unlike this the powder properties. Means, and what are all the factors which are affecting the apparent density? Apparent density of the metal powders depends on the density of the solid material, particle sizes, particle size distribution, and as well as the surface area, roughness of each individual powder particles, and the particle arrangements also gives us the apparent density and all, which is going to be strongly affecting the apparent density of the powder particle. Means the apparent density decreases with the decreasing size of the particles, and decreases as the particle shape becomes less spherical and more irregular, and also the decreases with increasing surface roughness, and as well as is increases frequently controlled by mixing of various sizes of the particles. Means if you control this apparent density, means we have to have the longer distributions of the powder particle sizes. Means that affects the particle size of the apparent density for several metal powders, which is analyzed by the ASTM B212 standard and all. You can see here the apparent density and average particle size diameter. You can see the size diameter is keep on increasing, even the apparent density is also increased with the different process. You can see the different apparent densities and as well as the particle sizes and all. And the true density we are measuring with this gas pincometer with the Archimedes principle, that is devised with the first method we are measuring, and even with the alflometer and caniclometer, as I showed you, measuring the cohesive strength of the powder particles. You can also use that the alflometer to measure the flowability. Means we are putting 50 gram of powder in this alflometer, and when we are counting the time to flow that 50 gram of powder, how much time in duration that is taking, 10 seconds or 12 seconds. Based on that, we are giving the flowability properties of the powders and all with based on this two ASTM standards and as well as metal powder industry federation standards. We are described this here. You can see this caniclometer and alflometer. And you can see the tap density always greater than the apparent density, because tap density is going to particles are packed more because of the application of tapping or vibrating under specified condition. It induces the movement of particles to lower friction between the particles. You can see here a spherical, irregular flake, 4.5, 2.3, and 0.4. And see the tap density always having a higher than the apparent density, because of the packing will be more when you are applying pressure or the vibration onto the particles. And the bulk packing factor and the flow properties. The flowability is one of the most important technological requirement for this the powders which are used in this additive manufacturing, and the density homogeneity of the final part depends on the layer by layer melting being formed on the thin and uniform layers that are accurately deposited and by the feeding of the device, whether it is the DED system or by the SLM system. The cohesive powders which exhibits poor flow properties are likely to more the problematic in terms of obtaining the homogeneous density of the layers throughout the build chamber, build layer, and powders which are comparatively more free flowing. Powder flow is difficult to relative to any one of the given parameters powder, but there are some general rules which can typically be applied for this powders and all. And the spherical powder particles are generally more free flowing than the irregular powder particles or an angular powder particles and all this final qualities depends upon this type of the powder particles and all. And the particle size is has a significant influence on the a flow and larger particles are generally more free flowing than the smaller particles. And a moisture content may be there in the pore particles that can be reduced by flow due to capillary forces acting between the pore particles. And for that, we need to like the reuse or the heat treatment we need to use for reducing such kind of moisture and all and all. Flow properties often show a dependency on the packing density at the time of measurement. That is, the pores with highest packing density having the less flowing and all. Like short range of attractive forces such as van der Waals forces and electrostatic forces that can adversely affect the flow and many cause particles agglomeration and all. That is in the a short range of forces having a bigger impact on the fine particles and all. Like in conclusions, if you see here how we can chemical compositions that can be measured with the laser sintering behavior of the metal powders would be not only that depends upon the physical properties, it will of course also depends upon the chemical properties of the powders and all. Like the relevant testing of the powder behavior and intrinsic powder properties at elevated temperatures also properly evaluated in the process performance like individual studies. And for more substantial understanding, we need to principal investigations are required of this powders and all, and that resulting studies will contribute more the fundamental standing and correlation between these powder properties and in-process behavior of the powder particles and all. And another aspect is like properties of the recycled powder. Whenever you are using a recycled powder, like up to this point, there are various powders which are analyzed, which you are using in the powder diffusion process. What I was suggesting around even 40%, but in DAD more than that 40% of powders are not in the melt pool and all, because of the sputtering, because of the ejection, the powders are coming out of the melt pool and all. In such type of powder, we have to reuse and reuse for this, especially for recycling of the powder. Means these facts that make use of the powder bed fusion is potentially a resource efficient process, and efficiency extends strongly depends upon the conditions of this unmelted powder particles. Therefore, recycling of that powder process part properties is mainly focused on numerous facts and all. That we have to use that received powder with a mixing with the original powder. Like each build is a consistent of the proportions. Like we need to proper proportions we have to use, like with the received powder and all. Otherwise, we need to have the lot of difficulties in fabrication, or we are going to have lot of porosities or defects in the fabricated part and all. If you have any queries with respect to this powder production, powder properties, I'm happy to address your queries. Thank you for listening my lesson on this powder production and powder characterization, which is especially required for additive manufacturing process and all.
Well, participants, now we are open for this discussion. So please ask your queries. You can unmute yourself as well as you can type your question in the chat box. Yes, please, participant.
Is there any questions from the participants? If you are expecting what kind of powders are required for your additive manufacturing process and all?
Yes, please ask your queries. Anything related to this powder characterization for additive manufacturing processes, please.
Good morning, sir.
Yeah, good morning.
Sir, many of the in the fabrication, so the size of the fly ash is approx the 100 micrometer. So how to reduce the size?
Sir, your voice is breaking. Could you put in a chat box? You are telling something about 100 micron of powder. I do not understand fully what is your question.
Okay, sir.
Vishal sir?
Yes, sir.
Yeah, can you repeat that question, sir? What is was asking?
I think he's asking like powder which having size of 100 micrometer and further if they want to reduce it, how they can reduce the size.
Sir, if we are having a powder of 100 micron, if you want to use it for again for the additive manufacturing process, we can use with the plasma electro-rotating automation process. Again, we have to minimize the size of the powder and then we can use it. Otherwise, we can go with the ball milling process. What happened in the ball milling process? See, size is going to be reduced, but the deformation of the particles is going to be taking place, and powder geometry, the sphericity is also going down. Because of that, many people, if you want to reduce the further size, they are using the automation process to reduce the size of the powder particles.
Well, I hope you have got your answer. Well, still, if you have any doubt, you can type your question. So, once again, I request all the participants, whatever the queries you have, you please unmute yourself and come forward.
Sir, am I audible, sir?
Yeah,
Is it
yeah,
Yes,
Alok
sir,
Mishra, sir?
audible.
yeah, sir, audible, sir.
Sir, I have a query regarding this bulk packing, sir.
Yeah.
Is there any thumb rule or any visual parameters by which we can say that bulk packing is proper or not?
What we can do, sir, by seeing this flowability properties with the alphameter, you can see what is the bulk properties of this powders and also. Like SLM, the bulk packing is very much important, sir.
Sir.
That's why how we can see once it is the powders are manufactured with any automation process, or you might be procuring from outside also. After that, what you have to see first the flowability and then the morphology of the powder particles. And if the size distribution is very small, and if you are having a very uniform spherical powder particles, then the bulk packing factor will be very good, sir. Those things you have to study. If the powder is not flowing properly, normally flowability will be good when you are having 10 to 12 seconds to flow 50 gram of powder. If it is taking more than that 10 to 12 seconds, then the flowability is not much good. We need to see some other addition operations to increase the flowability of the powders.
Thank you, sir. Thank you very much, sir.
Thank you.
Good morning, Dr. Manjaya.
Yeah, good morning, sir.
I'm Chandramohan here. Very interesting presentation. I have a clarification.
Yes, sir.
That is it any, do we have any standards, international standards, specifying the specific process for the types of alloys being used in this additive manufacturing? Like, for example, nickel powders we are using, titanium we are using.
Yeah.
So is there any standard available, like international standards available for international standards developed for the specific alloy in a specific process?
Sir, actually there was no standard is available, sir. What we can do with the automation process, we can manufacture whatever kinds of meltable metal powders. All these kinds of powders can be manufactured with the only thing we have to take care of the oxidation effects. If it is oxidizing material like Inconel materials or the aluminum or the titanium materials, we have to think of the better to go with this gas automation with inert gases, argon or nitrogen. And if you want still more very fine the particle sizes, geometry, sphericity, you have to use the plasma automation processor. But there is
Okay,
not
as now
actually any
the
standard is available, sir.
okay, as now the standard is not developed.
Yeah, yeah.
Right. Thank you so much.
Thank you.
Yes, please. Any more queries?
Even sometimes we have tested with some ball milled powders with this DED process, and we are trying to we check the flowability properties of such type of powders, but the powders were not flowing properly. But even still, we have tested. I will share some of the information you can see here. The powders are manufactured with the ball milling, that is the intermetallic powders. It consisting of that both ferrous materials and some high temperature materials also there. Such type of powders we are fabricated with this ball milling process, and we are check the flowability. Flowability is taking more than 15 to 20 seconds to flow around 50 gram of powder. During that ball milling, what happened? There are a lot of agglomerated or some bigger size powder particles also there. To sort it out, we have done the sieving process. Sieving we have done very clearly with the different size of the things and all. And then after that, we have analyzed this powders. Then with the suddenly once lump of powders is flowing in the flow meters and all. Such type of powders we are fed into the system with the DED system, and then we have measured how we can able to use. Can you able to see my screen, sir?
Not yet.
No.
Just shared. Can you see, sir?
Yes.
Yeah.
Yes, sir.
You can see such type of powders we are used to with the DED systems. What happening is spattering is more, and the bead formation is not uniform, because there is a lot of balling effect is going to be taking place in when the bead formation is taking place in the layer by layer when you are depositing. Such difficulties are taken place, and if you see a different kind of with that we have finally efficiently fabricated the part, but still there are a lot of challenges occurred in these kinds of intermetallic powders when you are using with the ball milled powder. You can see a lot of cracks are there in the build direction, because we cannot able to control the solidification rates. You can see the different trials we have made. You can see the delamination has taken place, a lot of cracks, even this the surface layers are sudden solidification is taking place. Even though efficiently we have fabricated the walls, there are a lot of difficulties, defects are occurred in these kinds of ball milled intermetallic powders and all. These are all challenges when we are using this ball milled powders in the additive manufacturing process and all. Any other queries?
Yes, please participant. Any more queries?
Even you can see here, if you are having a different such type of powders, the ball mill powders, you see at the first condition with lower laser power of 500 and with higher scan speed, we are assuming 1.5 gram powder flow rate. You can see there is no formation of weld bead at all. You can see then what we have tried, we have reduced the laser power and reduce the scan speed, and you can see still even we are keeping the constant of the powder flowability, there is no formation of the uniform the weld bead in the substrate end because the powders are not uniformly flowing. That is the major challenging issues, and then we have tried still so many trial and error with different things, then finally we are able to build, but still the delamination crackings are occurred in this such kind of powders, intermetallic powders. That's why the major thing in IT manufacturing is what kind of powders we are using. That is very much essential. You need to have a spherical, highly efficient spherical powder particles of uniform distribution. That is when we are using SLM 5 to 45, and when we are using with DED system 45 to 90 micron is suitable.
Yes, any more queries? Yes, participants. Well, if you don't have any query, then
Dr.
yes,
Manjia, I have
Yes, sir.
a clarification. Till a few years back, there were no much successful suppliers of powder. I mean, other than the original OEM. But now, how about the condition? Is there more supplier in India who are doing successfully? I mean, regarding the quality of powders.
Sir, in India now the suppliers are increasing. Sir, now Weldwell is giving all kinds of powders, and Praxair they have started branch in, I think in like in Mumbai and as well as in Madras. Praxair is a US company. Especially they are manufacturing this stainless steel powders and aluminum powders. And when you want to go for like non-ferrous like Inconel and other kinds of materials like titanium materials, Worldwell is supplying, and as well as another company that is recently started with this Indomim collaboration. They are also supplying such kind of powder materials, sir.
Okay.
But even though cost is around 30 to 40,000 for per kg of titanium, sir, but that is the major difficulties for this powders and all, sir.
Thank you. Thank you.
Thank you. Oganas is the most major leading companies for powder manufacturers, sir.
All
But
right.
they are not supplying in India and all, sir.
Mhm. You know, even CSIR, there in South Africa, they tried a lot, and I think till now they couldn't come out very successfully, like
Yes, sir.
OEMs.
Yes, sir. Even this MG Sales Corporation, they recently started in Hyderabad also, but it's a like outsourcing the suppliers, sir. They are procuring from somewhere and they are giving to the R&D labs or institutes and all. MG Sales Corporation.
Okay. Fine, thank you.
Thank you.
yes, please. Any more queries? Yes, please. Last call. Otherwise, we are going to close this session.
Vishal sir, hope you received my MCQ email, right, sir?
Yes, sir, we have received. Well, then I think it's all over from participant side. So, on the behalf of Mechanical Engineering Department NIT Silchar, I extend my sincere thanks to Dr. Manjaya for allotting us his precious time for this faculty development program. And today we had this wonderful opportunity to hear your talk on additive manufacturing, and you give us a in-depth knowledge into the topic of this powder processing and characterization for AM applications, and also revealed some very interesting facts. So, sir, this will surely going to help us in our future research work as well. So once again, we are very thankful to Dr. Manjaya for his valuable time and for his wonderful talk. So thank you so much, sir. With your permission, I would like to close this session now.
Yeah, thank you, sir. Thank you for providing me opportunity to deliver my research work in this faculty development program. I will thank Yogesh sir and as well as Vishal sir and head of the department of NIT Silchar and all. Thank you very much, sir, and thank you for the participants.
Excuse me, sir.
Thank you so
Excuse me,
much,
sir.
sir. Yes,
Nigel,
yes,
sir. Sir,
yes.
please request sir to switch on his camera so that I can take a group photograph.
Okay. Yes, participants, it's a request. Please switch on your camera so that we can have this one group photograph. Yes, participants, please switch on your camera. Yes, please, it's a request. As it's a mandatory thing for this ATAL FDP programs, we need photograph for each and every session. So let's have a one photograph. Yes, Vishal, have you taken?
Yes, sir. Yes, sir. Almost over.
Okay. Then thank you very much. Thank you very much, sir, once again. So with your permission, I'm going to close this session, and we have next session from 11:45. So we can have this, 15 minutes break, and we'll meet.
Thank you, sir.
Thank you, sir. Thank you, Dr. Manjaya.
Yeah, have a good day, sir. Bye bye.
Have a good day. Yeah. So please take 15 to 20 minutes break. Then we'll meet once again at 11:45. We have next lecture in line. So thank you very much once again for joining us.
Rajiv sir. Hello. Hello.
Hello.
Rajiv sir.
Yes, sir. Yes, sir.
Yes, sir, he's coming. Just coming. Just wait.
You started session or it is late?
Yes, sir.
No,
Just
no,
we
sir has joined. Dr. Dave has joined, so we are just going to start.
are going to
Okay.
start.
Okay, sir. Okay.
Okay. Good morning to our expert, Dr. Harshit Kedave, sir, and good morning to all the participants. I am Dr. Rajan Gupta. As a coordinator of one of the coordinator of this event, I welcome you once again in this current session, which is going to be right now within 2 minutes. Okay. Dave, sir, can we start?
Yes, we can start, sir.
Okay, sir. So, before starting this session, I welcome Dr. Harshit Kedave, Associate Professor from SV NIT Surat, Department of Mechanical Engineering. Just before starting this session, I would like to give the brief introduction of Sir to all the participants. Dr. Harshit Kedave is the Associate Professor in the Department of Mechanical Engineering, Sardar Vallabhbhai National Institute of Technology, Surat. He has completed his PhD in Mechanical Engineering in 2012 from SVNIT Surat, Masters in Production Engineering in 2003, and Bachelor's in 2001. He has more than 15 plus year experience. His research interest is unconventional and micro machining processes, 3D printing and additive manufacturing processes, fabrication and characterization of composites, modeling and optimization of manufacturing process. He has also research and consultancy project worth 5 million undertaken. He has published 15 book and book chapters. He has applied for 12 patents. Out of 12, 3 has been granted and 9 is under consideration. He has published more than 125 national and international journal papers in the national and international reputed platform. He has the supervisor of 7 PhD students, out of which 3 has completed and 4 is undergoing. He has guided more than 30 MTech students. Dr. Dave has organized 15 conferences, seminars, training programs, etc. Apart from this, he has also delivered more than 50 plus lectures in various events in the different national and international events. He has also the professional member of like secretary in the professional association in modern manufacturing technology, life member of Indian Institution of Industrial Engineering, life member of Additive Manufacturing Society of India, life member of Indian Society of Technical Education, member of Indian Institute of Welding, and member of Indian Society for Non-Destructive Testing. So the sir is with us to give his expert talk on the topic 3D printing of composite. I hope the sir will just give you all the gist which can be summarized in within this 2-hour time, and the participants will take full advantage of this session. Sir, I am inviting you for to start the session. Hello, am I audible, sir?
I wish to thank switch off the web. It's all across India.
Hello. Sorry to interrupt you, Harshit sir. Hello. Am I audible, sir? Hello. 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 David sir, am I audible? Actually, there is no voice from your side.
Hello. Am I audible,
Hello.
sir? Hello.
Yes, you are now audible, sir.
Okay.
Yes, sir.
Okay. Sir, what I'll do is I'll keep video off. Probably
Yes, sir.
that
Yes,
is
sir.
preventing some sort of streaming.
Definitely, sir. Please just off your video and you can proceed with just audio only, sir. Because it is
Sir,
creating
now
problem.
is my first slide visible, sir?
Yes, sir. Yes, your first slide is visible. Please make it full screen and just you can start with that only, sir.
Now full screen?
Yes, sir. Full screen now.
Fine, fine, fine. Okay, okay.
Okay.
Please interrupt me in case if I again get my voice gets disconnected.
Definitely, sir. Definitely.
Okay, so I'm sorry for the small glitch at my end. So today I'm with you to share some of my views on 3D printing of composites. I come from the western end of India, and Surat is situated on the Arabian Sea. And one of the fastest growing cities in India. And we are proud to be associated with the name of Sardar Vallabhbhai at our place. Surat, as you know, is known for diamonds and textiles. About 97% of the diamonds in the world are processed in Surat. Over and above that, we are one of the largest producers of synthetic clothes in India. Many heavy engineering industries like Reliance, like L&T, like ArcelorMittal, ABG Shipyard are situated in and around Surat. Ours is an institute which was established in 1961, and we are celebrating our Diamond Jubilee this year. And I'm very much happy to be associated with NIT Silchar today through this training program. These are some of the topics which I wish to discuss. Briefly introducing composites and the traditional manufacturing processes, I'll move to 3D printing of various types of composites like the fiber reinforced composites, the polymer nanocomposites, the polymer ceramic composites, the polymer metal composites. And finally, I'll come up with some research scope as on date in the area of 3D printing of composites. As we know, composites are engineered or naturally occurring materials which are made up of at least two different constituents which have different physical chemical properties, and they remain separate and distinct at the microscopic level in the final structure, but together they contribute towards the improvement in the overall properties and capabilities of the composite structure. Composites are widely applied in different industries like aerospace, like automotive parts, like civil engineering structures, like sport goods, like energy production equipment, portable power sources, acoustic instruments, and yes, textiles and paper industry. Basically, traditionally, when you produce there is yet the fiber structure fabric. We need hello.
Hello.
Am I audible, sir?
Sir, actually your voice was breaking, but right now you are audible.
Acha, okay. Please let me know in case if there is any problem.
Okay, sir. Okay.
So such traditional processes require higher skills and greater costs are involved into it to produce these composites. 3D printing as on date is an alternative manufacturing method wherein we are able to produce highly customized parts. We are able to produce highly customized parts through the same method wherein we are able to create structures with complex geometries. So as far as geometries are concerned, we have better using the 3D printing process. The processes which are being used are out of the 8 different 3D printing processes. 4 are basically used for 3D printing of composites based on date. The chief among them being the FDM process, followed by SLA, the LOM process, and the SLS process. When we talk about the FDM process, here certain fibers like carbon and the glass fibers in the continuous condition or in the chopped condition, they are being printed through the nozzle. There are different ways of doing it, which I'll discuss in the coming slide. But a major problem that comes up in the FDM of fiber-based composites is the clogging of the nozzle. So when composites are to be printed, specifically designed nozzles of slightly larger size are required. Then there are some problems in printing of the fibers, wherein the interlaminar strength is often observed to be less. I'll discuss with some example in coming slide. In case of the photopolymerization process, especially the SLA process, here it is not possible to use the continuous fiber to a larger extent, but usually short fibers or fiber mats are being utilized, wherein if the fiber mats are being utilized, once the layer of resin is put up, this fiber mat is placed on it and then it is being cured. Whereas short fibers are very tiny particles which are evenly mixed into the resin. And after evenly mixing into it, the process is carried out as per the usual method. In case of laminated object manufacturing process, the feedstock material is usually in the form of a fiber sheet. So these are pre-packed sheets having fibers reinforced in, and this is being wound and unwound over the table. And as per the design of each layer, this is being cut and the layers are being generated. However, this process is not that effective, so not major people are observed to be working into it. When we talk about the fiber reinforced composites made by SLS process, this probably is an easier version, because just as the powder of the polymer that we use, we are able to use the powdered fibers, micro scale fibers, be it the carbon fiber or be it the glass fiber, that is being mixed in the selected proportion with the powdered polymer, and then this is being cured by the usual lesser source. So this process in a way is a bit of faster process also, and it gives better results also. Generally, polyamide and polystyrene thermoplastics are being used as the matrix material in the process. Now, I the
Sorry
And
to
on
interrupt
this,
you, sir.
yes,
Yes,
hello,
yes, yes. Now
hello.
your voice is coming.
Uh, I think I'll change my my.
Hello, sir, am I audible?
Yes, sir. Now that is clear.
Yeah, so I just changed my headphone. Maybe that is creating the slight trouble.
Okay, sir. Okay.
Let us see how it goes. Okay,
Okay.
so I'll begin this slide again. As I said, the first layer of fiber, as usual in the FDM, is printed, on which we place the usual carbon fiber, and we create another layer over it, and layer after layer the part is printed. Now, an interesting work is reported by Mori and his team, wherein these parts, usually the polymer printed parts, we do not heat, but they slightly heated. They came across a wonderful observation. Usually, when there is no heating done at that point of time, there is no proper bonding between the fibers and the polymer. So you can see that when tensile testing is done, when the part is broken, the fiber portion comes out of this. So here it is separated and it comes out without disturbing the structure of the polymer. Whereas when thermal bonding is carried out by some heat treatment, it is observed that the polymers and the fibers interact very well with each other. And when testing is done, it gives you better strength, as well as the breaking of the fibers along with the polymer is observed. So it is in a way it is attempted to create a better bonding between the fiber and the polymer while printing them one after the other. The other strategy which we use is by embedding the fiber into the filament itself. So what you do is you use the polymer, and you mix the chopped fiber with it, and you extrude it through the extrusion process. I'll discuss this in the later case. So this extrusion is being done, and you can generate a composite filament and use this filament directly for the printing of the parts. So in a way, I'll discuss this in a different form in the later slides. In a way, the extrusion process and mixing of the fiber and polymers, we face usual problems of the proper bonding between the materials. However, if that can be done effectively, printing becomes a very easy task, and it gives better strength to the parts as compared to the other methods. There is an interesting observation of this particular case reported by one of the research group. This is the clear ABS part, neat ABS part. And when this is being printed, it is observed that interlayer spacing is large. So this space that we see, this one is in the tune of 100 microns, and it porosity often observed to be same, because the particles in a layer, in an individual layer, these fiber particles, they have some porosity around. So effectively they are dispersed well, they reduce the inter layer spacing, and that is how they help to increase the strength. You can see the strength is absorbed, is increased. And when you compare it with usual aluminum 6061 alloy, the strength of this 30% carbon fiber infused ABS is higher than what aluminum is showing. So in a way, this fiber can injected together, and when it comes out from the nozzle, it comes as a single material. So what happens is you have a polymer, and inside the polymer, more or less somewhere in between, in one case it is observed that the fiber remains on the side, and so it is not that effective, but often it remains totally inside the polymer material, and that is how it can be deposited on its respective layer. Similar observation, similar work has been reported by a team led by Tian, and it is found that you need larger size of
Hello. Sorry to interrupt you once again, sir. There is audio problems right now. Once again.
again.
Yes. Now it is okay.
Okay, sir. Okay, sir. Probably I feel that there is some
Not audible, sir. There is network issue.
am I audible?
They're not audible, sir.
Hello.
Yes, sir. Now it is audible.
I think there is connectivity issue, sir. I've just requested my student to have another connection and another laptop. In case if required, I'll switch over. I'm really sorry for the trouble, sir.
Okay, that's a no issue, but because then the WebEx says is issue with video audio, I don't know what is the problem.
Yeah, probably there is streaming issue, I suppose.
Yes.
Sir,
Because in every 2 minutes there is a voice is not audible. Dear participants, I think there is some network issue with the expert. So please be here. He is going to correct once again.
Hello? Hello?
Yes, sir. Hello. You're audible, sir.
Hopefully I remain audible.
Yes, sir. Yes.
So, okay, again, sir, is my slide visible?
Yes, sir. Your slide is visible.
In case if again network fails, I'll move to a from my institute connection, I'll move to a private connection. So then again, I'll take 2 minutes break in that case. આપણે બીજું ready રાખો. Hello? Hello?
Yes, sir.
Sir, am I?
Audible,
Okay,
sir.
okay.
You are audible.
Yes. Okay. Now, sir, this is the process where we keep the filament, the fiber as well as the polymer separate, and through separate nozzles we deposit them together as per the drawing. This work we have carried out at our place, wherein we use the Mark II 3D printer. And this in this 3D printer, the advantage is that the polymer and the fiber are printed individually. So they do not need to mix together with each other. As per the design, as per the drawing, they get deposited at the right place and they get embedded with each other. Hello.
Oh.
Hello.
Yes, sir. Actually, there is voice is once again breaking.
Sir, give me 2 minutes. I'm changing the system as well as the service provider also. So maybe that should solve the problem. I'm extremely sorry for the trouble, sir.
No issue, sir. We can understand, sir.
Just give me 2 minutes, sir.
Yes, sir. Okay. Dear participants, sorry to inconvenience. Within 2 minutes, expert will join once again. Please be connected here. Hello, dear participants. Am I audible to all?
Yes, sir.
Yes. So there is problem with the expert network. Okay. So please be connected. He is going to change his network, and soon he will join on. The audio is not proper from my side or his side. Can anyone tell?
Sir,
My
from
voice is
sir side. From sir side.
other side. Then okay.
Yes.
Hello, am I audible, sir?
Hello.
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 Sir, am I audible?
Yes, sir. Now you are audible.
Sir, full screen, board screen.
Yes, sir. Full screen is visible.
Okay. Please let me know if there is again
Okay, sure. Voice is breaking, sir.
Hello. Hello.
Yes, sir. Yes, sir. Actually, their voice is coming, but there is breaking.
Okay. Hello.
Yes, sir.
Hello.
Yes, sir. It is okay now.
Sir, am I audible?
Yes, sir. Yes, sir. Now you are audible.
Hello.
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 Yes. Yes, sir. You are audible.
Hello. Hello.
Yes, sir. You are
Hello.
audible.
Sir, am I audible?
Yes, sir. You are audible.
Hello. Hello.
Hello, sir. You are audible.
Hello. Sir, I'm audible. Hello.
Yes, sir. You are
You are
audible.
audible, sir. We can hear you as a participant.
Hopefully you continue hearing me. Hello. Hello.
Hello.
Hello. Sir,
Hello.
am I audible?
Yes, sir. You are audible.
Hello. Fine, fine. Okay, okay, sir. So this is the printer Mark II 3D printer which we are using at our place, and this is the printer with two separate nozzles. One is the nozzle for the polymer, and the other is a nozzle for the fiber. Through this different through different nozzles, the material is being separately placed on each and every layer as per the design. We are using two different materials. We use a specific nylon filament, which is commercially known as Onyx, as our matrix material, which has a diameter of 1.75 mm. As a fiber reinforcement, we are using carbon fiber, the glass fiber known as fiberglass, and it is also possible to use Kevlar fiber, and its diameter is 0.3 mm. So these two separate materials are being utilized during the process. Is this video visible? Is it streaming?
Yes, sir, it is okay now.
Yeah, so in this particular case, I would very briefly show how this activity is being done. So as I showed, it is possible to move the nozzle along X and Y through the Cartesian coordinate. This is the feed mechanism through which we can feed the polymer as well as the nylon. While doing that, it has to be ensured that the maximum movement of the X and Y is taken care of, so that there is no breakage of the material during the process. Now, when the activity is initiated, at that time, we utilize a specific magnetic table on which the material has to be deposited. So this build platform can be very easily removed, so that the task of removing the built part can be easily done. That is not usually possible on the usual FDM machines. So this is an advantage, so that even large parts, if printed, they can be separated from the machine. The build platform can be brought out from the machine, and it can be separated. As I showed in the image, here are the two separate nozzles for the polymer and the fiber. The fiber nozzle is made up of brass, while the polymer nozzle is made up of steel. Here, these are the two feed mechanisms of the fibers, which can be seen over here. So the smaller opening is for the fiber. So you can see the fiber spool is placed inside, and it has to be maintained through the process, so that initial way of passing the fiber through the feed mechanism is slightly tedious, though it's not difficult, but it takes some time for feeding it till this feed mechanism. Similarly, the larger feed mechanism is for the polymer. Now, the nylon-based polymer is absorbing moisture, so a dry box is required to be placed, so that the spool is continuously protected from the moisture. So during the process, we may use it, and after the process also it remains as it is in the dry box. So this is the polymer nylon filament that is being used for the printing of the part. Now, once this is initiated, you need very simple devices to initiate the printing, as well as to separate the parts. The major advantage or the USP of this process is related to setting of the process parameters. We can print the part on the flat orientation, wherein the part is placed flat on the platform. You can also print it on the longer edge of this part or on the shorter edge of the part. However, this is found to be slightly inferior quality as compared to the flat and on the longer edge. Further, you have the scope of having 3 different patterns. You can print the parts in a triangular pattern, in a hexagonal pattern, as well as along the these usual rectangular pattern. So this is also, there are 3 different ways of doing it. Now it is also possible to change the orientations and also to print in a concentric manner. So these are different ways in which the orientation of fiber and the polymer can be carried out. I hope I'm audible, sir.
Yes, sir, you are audible.
The advantage of this process is a very user-friendly software known as AICTE. This is a cloud-based slicing software specifically for this machine, and it is the main purpose of it is to avoid any sort of duplicate. So its design has to be done online, and when you use this cloud software, once that is done, the STL file and the printing codes can be downloaded on the system and can be utilized. It is possible to select different polymer materials. It is also possible to select different reinforced the fiber material, and once that selection is done, we also need to make selection of patterns, say triangular pattern or rectangular pattern, and what density we wish to have, that also has to be fixed up. The software is capable enough to suggest the most optimum setting. So if we wish to go other than the optimum setting, that is also possible. But however, it will make a suggestion of taking up certain specific conditions. In reinforcement, we can decide the fill pattern, and we also can decide what would be the outer rings. Do we want it to be from the polymer, or do we want it to be from the fiber? And how many such rings we wish to have, that also can be fixed up. Similarly, the angles at which we wish to have the inclination, that also can be fixed up. Now see, once you save this selection, on the part details, it will give you the dimension, how much time it would take, how much material would be utilized, and so as per the convention, what would be the cost. If there are any mismatch in our selections as per the software, then that suggestions are also given. We may accept those suggestions or we may ignore them while printing. However, these warnings are given to select the optimum parameters. So this is how the software works, and the selections are being made. Now, the other thing is, once the part is made, it is possible for us to go through 2D or 3D view, and it is also possible to see each and every layer. Say, for example, this particular part has 32 layers. Each and every layer is visible to us. Now, if we want to make some changes in some specific 3 or 4 layers in between, then we can select those number of layers and make some changes in their parameters. So that possibility also is provided. So individual layers, if required, while deciding the final STL file, it is possible. So right now we are seeing, say, 22nd layer or 26th layer right now. So how we will see the polymer material. The gray color indicates the polymer and yellow color indicates the fiber. So in one particular case, this is how it's being done. Now, when the program, the drawing is ready, and when we import it, we download the program. Then what we do is we initiate the printing. Now, generally, sir, am I audible? I hope I'm audible.
Yes, sir, you are audible. Video is going. So
Yes. Okay. So we may select the program that we have downloaded, and as per the requirement, temperature of the nozzles would be set up. So specific temperature once achieved, then this is a usual practice in FDM. The build platform will move to its position, and then after each layer it will keep on moving downwards. However, this movement is highly precise with the good quality of the mechanism. When printing is initiated, first what it does is it creates a trial print first as a boundary where inside which the final printing of the part will be taken care of. Let's slightly skip this. So this is how the printing is being done. We can see the fiber laid. You can see the white color glass fiber and the grayish color of the polymer which is being printed. So this is how it goes on, and you can see the fibers are being placed on the layer. This is the triangular pattern which is being created. Because we have made lesser density, so there is a good opening. But then once we want to place the fibers, it will create a base structure first, and then it will put up the fibers on it. So this is how the entire part is printed, and then we can easily separate it from the setup. So as I said earlier, it is very easy to remove these parts as compared to those which we remove on conventional regular FDP process, because we are not able to usually remove the build platform outside. So this is the part which is being fabricated. The same part was for tensile testing, so we carried out the testing of it, and this is the internal structure which we observe on a vision measuring system. It can be easily seen that we had placed the outer rings. So these outer rings are also visible, fiber rings. We have a notch being placed, so at the notch you can observe their part. Internal structure is placed in a rectangular fashion at 45 degree, so that is also visible, and whatever space remains empty while placing this fiber, that is again filled with the polymer. So this is how the entire part is printed. After doing this, we have initiated studies, right? Done some studies on impact as well as tensile. Flexural parts are still under printing right now. Using the ASTM D638, we have created the tensile specimens. We had 32 layers. We tried to ensure that around 30% of the fiber volume fraction is ensured. It is observed that when we print the parts with the only accent is the only nylon material, the strength is quite less as compared to what we observe with the fiber class. One is the simple fiberglass and the other is the high strength and high temperature fiberglass. Though it takes larger print time as compared to the simple nylon, we observe that the strength is drastically improved. The tensile strength is drastically improved. However, what we observe is that the simple nylon material, though it shows the lesser strength because it goes for higher deformation and under the ductile failure, whereas these two materials with the fiberglass, two different types of fiberglass, they usually fail and their strain does not exceed 0.35, and it fails under the brittle failure. This is evident from these images. The reason behind this is that only nylon material gets deformed and it fails at a particular level, whereas in case of the fiber-based nylon, wherein it has the glass fiber in it, we observe that these fibers are distinct and they break at a particular load. So under different conditions, we observe that they break and result into the brittle failure. Similarly, we carried out impact testing using ASTM D256 standard. Again, we tried to ensure that the fiber volume fraction remains close to 30%. And what we observed is here, here also there is a drastic improvement in the impact strength of the fiberglass based nylon material. However, as compared to the tensile test, we observed that the fiberglass has better exhibits better strength than what the high strength, high temperature fiberglass shows. So that is evident from the value of the mean impact strength that we see. This is largely because we observe that when these fibers are being printed, they are laid at different inclinations, and because of that, the failure does not occur very fast. However, whenever this occurs, this results into the instantaneous failure. A similar task by the same process on a larger machine is being demonstrated by a big area additive manufacturing system, which is developed at Oak Ridge National Laboratory in USA. And what they are able to do is the same process which I just showed. They are able to print full-scale aerospace parts out of it. So the size is evident from the image. Similarly, a US startup known as Local Motors, they have printed the entire structure of a car, of an electric car, in a single go by using this particular procedure, utilizing the nylon-based filament and the carbon fiber. They have used the carbon fibers into it. Now I come to the second part of my discussion, which is the polymer nanocomposites. I'll try to slightly gear up because I have lost some of the precious time while making this, taking care of the connectivity. In case of polymer nanocomposites, what we do is we add certain nanomaterials like the graphene, the CNT, and the other nanoparticles from metal or from the ceramic into the polymer matrix so that a better quality composite can be generated. Nowadays, graphene is being used in almost all the processes like FDM, like SLS, like SLA, and it is giving some remarkable electrical, mechanical, and thermal property improvements. We attempted carrying out this task wherein we used the graphene nanoparticles and mixed it with ABS as well as with PLA polymers, and through the single screw extruder system that we have, we were able to create the filament. We used this filament for 3D printing. We tried different combinations of the barrel temperature as well as side temperature, and eventually we settled at one particular combination where it was giving a uniform 1.75 plus or minus 5 micron dimension of this filament. We tried to print 3 different conditions with 1% graphene, with 3% graphene, and with 5% graphene. And we observed that as the percentage increased, we observed that there was a reduction in the tensile strength. No specific trend was observed for the flexural strength. Our intention was to obtain some part which could exhibit electrical properties. To some extent, we succeeded in doing it, but however, because of the agglomeration of the graphene particles inside the polymer, probably that resulted into slightly poor quality of the filament, which did not improve the mechanical properties, as well as it did not give the electrical properties as per the intended objective. So right now we are trying to work on it and trying to improve it so that we are able to achieve both of these properties simultaneously. When we talk about the ceramic based composites, the polymer ceramic composites are very much useful in various biomedical applications because often they are biocompatible, they are highly resistant to corrosion, and the best advantage is that they are flexible. So different types of ceramics like titanium oxide, zirconium oxide, aluminum oxide, calcium ceramics are used as reinforcement materials with various polymer matrix, usually polyamide, polypropylene, and PLA. One such activity is being carried out by Jacobs and his team, wherein they have tried to resemble the cross section of a bone, and so for a specific bone graft application. And they observed that this polymer ceramic composite is highly flexible, and at the same time it is giving better strength. So under compression, this is it is visible that it is able to resist the compression, and once the load is removed, it regains its shape. So that way this becomes highly useful material. Not only that, when attempt is made to try for finger compression, that is also possible. So you can see that it gets compressed well, and once the load is removed, it regains its original shape. So there is a good possibility to work into this field for specifically for bone graft applications, because we also need to take care of weight and we also need to take care of the strength simultaneously. Similarly, there are many applications of ceramic based composites, like it can be used for making bioceramic scaffolds. It can be used for making photonic crystals. Attempt is made to print very micro size of hollow turbine blades, small size of impellers, and various applications for investment casting. These are very tiny parts, and they are effectively used at different applications. So polymer ceramics, yes, they are exhibiting good strength at different applications. However, one care that is required is that you need to change the material for nozzle. Usually the nozzles that we use are made up of brass. However, for printing ceramic as well as metal based composite filaments, a hardened steel is preferred as compared to the brass material. Similar to what we try for ceramics, attempts have been made by people to print different polymer metal composites also. This particular material is able to exhibit properties like adhesiveness, flexibility, like conductivity, like processability, like toughness and strength when you mix metal particles into the polymers to make PMCs. Large scale activity is being done by different researchers. However, there are limitations into it, because when you mix metal powders into polymers, there are issues with the viscosity of these filaments to flow during the FDM process. So with certain specific composition of additives, it is possible to take care of it. However, from case to case, from metal to metal, from size to different particle size, these different additives, the type of these additives as well as their proportion is varying. So there is a good scope to work into this field, wherein for specific particles as well as specific grade of these particles, it is required to come across the specific proportion of the additives to be mixed into it to take care of the viscosity. Usually, most commonly, aluminum and iron powders are widely attempted with the help of ABS, polypropylene, and polyamides. There is a scope to work on the other combinations also. So if I try to sum up this discussion, there are certain advantages of 3D printing of composites as compared to traditional method, especially on what FDM process offers. So the first and foremost advantage is that we do not need any sort of molds. So the requirement of designing and fabricating these molds is totally avoided. The other major advantage is that we generally do not have any scrap. No wastage is found at the end of the process. Another time-saving advantage is that almost there are no post-treatments required. And finally, we can avoid human mistakes because these processes are automated. There is very less human intervention when the composite is being printed. So this advantage is so we are able to save time, we are able to save material, and we are able to improve the quality automated process. So in a way, this leads to a better deal as compared to the traditional procedures. As I discussed, we are now in a phase that environment has become a very big issue. So attempt should be made. There are people who have started, including few in India also. And the possibility of generating natural fiber reinforced composites because there it has a huge potential in India, and also it becomes a very environment friendly material. A possibility is to add various metal particles and maybe mix of different metal particles into the polymer matrix. That also has a scope of study because with the advancement of technology, people would be fast replacing the materials which are being fabricated, and I believe that these observations these results will help in coming up with newer materials. Several studies have been reported where polymer composites are being built. But when you talk about the nanoparticles mixed into it, there is a good scope of further studies into it. So these are different opportunities of working into this field. These are few of the references which I have used in preparing this presentation. At our lab, we work on different 3D printing processes like FDM, like SLA. We print composite materials, we fabricate our own filaments, we are blending different polymers, and we are trying also attempting to make nanocomposite materials. I would suggest you to visit virtually with our group at YouTube as well as Facebook using Manufacturing Research and Innovations Group. And yes, someday when the things get normal, I would definitely wish and invite you to visit our laboratory in person. With this, I end my session. Thank you very much for the exemplary patience that is shown by you. I regret the glitches that we had during our session, partially because of the poor internet. So thank you very much. Over to you, sir.
Okay. Thank you, sir. Thank you for your nice presentation. Although there was some audio issue, but overall the experience was good. From my side, that is, I think all the participants has gained the broad view of this presentation in the proper aspect, because there was some issue with the network. We all know that there is some always network issue with us also. So, but overall, this session was very good.
Sir, I made this presentation to my students also. So I have the recording of this session with me. So I share that with you, which you can share with the participants. So if required, that can be listened again, so that this break which I also had, I might have missed many things which I wanted to speak because of this break. So I'll share that presentation, that video presentation, which you please share with the participants. I'll also share this PPT with Dr. Yogesh, which can be shared with the participants.
Hello.
Hello. Hello.
Yes, sir. Definitely.
Yes.
Thank you for this. Your this word that you are sharing the PPT and the video. Definitely, we will share with the participant who is really interested to work with that. Okay. Thank you, sir, for this nice session. Now,
Sir, I have a doubt, sir, regarding this, composites.
Yes, sir.
Sir, excuse me.
Yes, sir.
Definitely. The session is now open
Sir,
for query. Department can ask the question.
Okay, sir. Thank you, sir. Sir, if the large parts has to be printed in 3D printing, the printer from edge to another edge, it's a long part. So, if the printer is printing on other side will be dry up easy, fast. Na? So, when the printer moves again to this edge, it can bind. How much there is a binding effect will affect the sizes, sir. My question is
yes, I got your question.
Okay, sir. Thank you.
What you are asking is, when you are printing a large part, so from one end to the other end when you print, so when the printer is printing on, say, left end, the part which has been already deposited on right hand, that would be solidifying fast. So when the next layer comes on it, it is altogether a new layer. So how bonding will happen between them?
Yes, sir. That's my point.
This probably is your question, right?
Yes, sir.
Yeah. So the
Exactly.
thing is, what happens is, when you observe this in FDM, specifically, this is a problem for FDM. In case of if you take SLA, or if you take, say, photopolymerization, or if you take SLS or SLM, this will not be a big issue, because the laser travels at a very faster rate all across the layer. However, when we are trying to print in case of FDM, there are two issues which come up. Number one is the first layer, which is already getting solidified, it would slightly spread along the horizontal direction. So when the next layer comes over it, it may take time to spread across it. So what happens is, we observe larger scale effect on a larger component when the part to be printed is large. So scaling, the staircase effect will also be large. And the other thing is, the heat that gets transferred from one layer to the other layer, subsequent layers, is reduced, because the part has already lost the heat. So the strength in such cases might be an issue. The other problem that we may observe is the part might slightly get warped. Warping we would observe, so that because of that, the next layer may not get printed over it. What I'll do is, when I'll share my this PPT, after thank you slide, I'll add 3-4 more slides. I have such samples where this effect is observed. So I'll put up those images into it for the better reference. I think if you go through those images, those photographs, I think you will understand better. So in case of FDM, yes, you are right. This is a big challenge and issue. However, in recent times, certain OEMs, one of them being Divide by Zero in India, and the others, what they are trying to do is they are trying to increase the speed of this printing. So while doing that, they are taking care of two things. One is the XY movement of the nozzle is slightly faster, and the other thing is they provide their own raw material, their own filament, which has faster solidification. So the entire process becomes faster, and these issues, these errors, these problems can be
Sir,
avoided.
can we print these large size components with more than 1-2 nozzles, printing nozzles, sir? I mean, at a time, one nozzle print other side and one nozzle print other side, sir. Can we manage like that?
That is possible. Certain service providers which use multiple nozzles. However, that is not that widely. Those machines are not that widely available. So I was just seen a few videos on YouTube wherein multiple nozzles are doing it. One problem that you might encounter is in maintaining the connectivity between the same layer. So
Yes,
see, half of
joining.
the layer is printed by nozzle 1 and half is printed by nozzle 2. Then wherever they come into contact, they may create slightly disparity in the layer, and so
Yes,
that may
connection.
result into non-uniformity of the layer. So that is an issue. Otherwise, people have tried to attempt it. In fact, HP has come up with one machine where you are able to print different colors of filament at a time. So you will have to use different nozzles for it. But I've just seen the videos. It has been recently launched, so I'm not sure and not aware about the quality of the parts.
Thank you, sir. So one more doubt, sir.
Yes, sir.
Sir, when a layer is printed on another layer, there is no any pressure on the top layer to compact. I mean, to join those two layers. Just they are joined only because of the bonding effect between these two layers only. That's it. I mean,
okay.
the bond
how
compact factor, there is no
the bond
compact.
is generated? How the bond
There's
is
only bonding
created
material, sir.
between the
It depends on the only bonding material, sir.
there are two aspects of it.
I mean,
one is what temperature you have set for the filament. Say, for example, if you are using PLA, the temperature is somewhere around 170 to 190. So if you can go for the highest possible temperature, it will have higher heat content into it. Now what happens is, by the time the already printed layer comes to the room temperature, so it has to lose the heat. Still, it is not at room temperature by the time the present layer is getting printed. So the bottom layer already has some heat, and this layer is also sharing its heat with the layer. That is one. The other thing is the layer that is put up is slightly sticky. That is not fully solid. That is not liquid. So it tries to spread on the existing layer. So when that happens, it is able to share the heat with the bottom layer, and that's how it instantaneously increases the temperature of the bottom layer, and that results into a bonding. And more important thing is, the layer that you are depositing, it also has its own weight. So that weight also helps to remain on the previous layer and create a bond between them. But yes, in FDM, to some extent, as the size of the part increases, the strength of the bond may reduce because of the disparity in the solidification of subsequent layers.
Thank you, sir.
Okay, sir.
Thank you very much, sir.
Okay, thank you. Dear participants, if you have any question, you may type in the chat box also, or you can raise your hand. I will unmute from my side so that you can just one-to-one interaction and you can ask the question.
Good afternoon, sir.
Good afternoon.
Sir, this is Vishal here.
Hello, Vishal.
Yeah. Sir, first of all, I want to tell that I am pleased to have you with a wonderful presentation, and I am thankful to you for that.
My
Sir,
pleasure.
yeah, sir. Sir, just I have one question that you have 3D printed a part, composite part using means continuous fiber and the polymer. Okay, sir.
Yes.
Sir, what if I want I want to blend polymer with chopped fibers and want to print an composite part? Sir, then there will be any specific size for the chopped fibers, or else we can take any size?
See, uh, this question probably has answer in two parts. Number one is the machine that we use uh, that has different polymer materials to be used as matrix, and these materials have either they are pure nylon or they have certain chopped say carbon fibers mixed into it. So that type of material is readily available. That is one thing. The other thing is, if you want to create your own filament, where you want to mix these fibers, then it is up to the level of imagination and the capability of the processing that we may have. So whatever different size of chopped fibers we can have, the finer the size, smaller the size, the better maybe the results. So there is a possibility, yes, there is a possibility to work into that particular field, wherein you are mixing fiber powder or maybe very tiny chopped fibers in different proportions into these polymers and create the filament. However, as far as the machine that we use is concerned, it is not possible as per the software which it follows. It will not accept any foreign material other than what it uses. It somehow it is able to identify. We tried to put up our own filament of the same diameter, but somehow it is able to identify it, and it says that no, this is not the required filament material, so that is required to be changed. But on any open source 3D printer, it is possible. It is possible, definitely possible to create filaments. Nowadays, there are small size extruders also available, which take up the material as low as 500 grams. So you can have 500 grams of the polymer, and maybe if you want it to be 10%, then 50 grams of any other material, say the nanoparticles or maybe chopped fibers, and you can mix them and you can create a half a kg of filament out of it. So there is a good scope of working into uh, generating filaments for open source printers. And I'll tell you one advantage. Even if you buy a regular PLA filament, which comes from China, of course, that will cost you somewhere around 800 to 1000 rupees plus tax.
Okay, sir.
Now, if you buy ready-made filaments with various other things, different polymers or nanoparticles or fibers mixed into it, the cost would drastically increase. But my own observation is that the same PLA particle, the same PLA material which you get at 1000 rupees, if you are able to print say 10 kg material at a time, it will cost you somewhere around 200 rupees per kg only. So
Okay.
there is a good scope. There are certain local industries which are trying to adapt it. Professor Bhupinder Singh
NITTR. NITTR.
NITTL, yes, NITTL. They have attempted different grades of materials and they have successfully printed it. How far they have commercialized it, I am not aware, but there is a scope. If there are small scale industries or startups who can take this up, there is a huge potential in creating raw materials. And I'm open to get associated with anyone who would like to take it up on a commercial basis. Please get
Okay.
in touch with me in case if somebody is interested.
Okay. Okay. Okay, sir. Thank you.
Okay. Hello.
Yes, sir.
Dear participants, you may put your question forward to the expert if you have. If you want to type, so you can type in the chat box. If you want to just one-to-one question and answer your query, solution of your query, so you can just raise your hand from your screen. Just I will unmute you.
So in case if there are no questions right now, and if the questions arise after you go through the PPT later on, or maybe through the video, please you can write to me anytime. I would be more than happy to interact with anyone on this particular topic. We are also working on it. We are also learning. So in that learning phase, it would always be good to have inputs from researchers and students from all across India.
Yes, sir. Yes, sir. Okay. But just I think there is no question from the participants now. But whatever the PPT and your video you will share with us, then and we will definitely share with the participants. Thereafter, if
Fine,
they
fine.
find any
Yes,
kind
sir.
of query, so they may directly
Yes, sir.
ask you with your
Yes,
contact.
sir.
Provide.
Yes, sir. Yes, sir.
Yes.
Sir, this is Vishal here. One more question, sir.
Yes, Vishal.
Sir, can coating enhance the mechanical strength of a product? Suppose, sir, I want to extrude any filament. Suppose I take PLA as a filament, PLA pellet as a raw material, and I coat it, and after that I extrude it as a filament. So and 3D printed it. I got a product. Sir, can this product by coating we can enhance the mechanical strength?
See, actually, specifically, I'll share my experience. When we blended graphene with PLA. Now, graphene is we just use 1%, so that was very small quantity, but it has very high surface area. So when we mixed together, for even mixing, we used certain oils also with it, so that can be evenly mixed. Now, when that mixing happened, what happened is this graphene covered almost all the pellets, all the tiny pellets of PLA. So in a way, when we use nanoparticles, we are coating these pellets only, and when we print it, that is getting distributed in the filament. So yes, when you use nanoparticles, in a way you are coating these pellets, but then coating of, say, already printed filament, that is something which is interesting. I haven't come across any such study. But suppose if you have a filament and if you coat that filament and then you try to print it, what would be the outcome? Yes, that is something interesting. Maybe we can try. Yes.
Okay, sir. Okay. Thank you, sir.
Okay, thank you, Vishal. Is there any other question from the participants? I think there is no question in chat box also, and also there is no raised hand. So thank you, sir, for this nice session. I hope all the participants has got many information which is required for their research work as well as their study. So thank you once again, sir, to you for just
Sir,
delivering.
I'm very much thankful to you. I'm very much thankful to you for the invitation, and I sincerely regret the small glitches that we had during the presentation. I'm sure that it must have disturbed the attention of the participants, but then that was beyond our control at that point of time.
No issues, sir.
But I hope that can be slightly compensated with the video that I would share with the participants.
Yes, definitely, sir, definitely. No issues, sir, because this is the network issue that is we are also feeling sometimes it is very bad. So no one can control on that.
Yes, sir. Yes, sir.
Thank you, sir. Thank you for your session.
Thank you. Thank you very much, sir.
Now I request to the participants, you can have your lunch and we will meet again at 2:30 for the next session, okay, which will be delivered by Dr. A. Mandha Cherry. Okay. So we will once again we will meet at 2:30. That's the next session will be start from sharply 2:30. So please stay connected 5 minutes prior to the scheduled time so that we can start on right time. Okay, thank you, sir, and thank you, the
Okay,
participants.
good day everyone. Thank you very much.
Thank you. Dear participants, there is one. Hello. Dear participants, there is one announcement. We will share a feedback link to you over your email. So please just, this is feedback email. By evening, we will definitely share. And by tomorrow, 3 p.m., please just revert with us by filling that. So that we.
Good afternoon, sir.
So I welcome all the participants again in the session number 11. So this is the last session of this of the 4th day, and today in the session 11, the topic was design and manufacturing of patient-specific implant using printing. That is to be delivered by Dr. A. Manmadha Cherry sir, Assistant Professor of IFHE University, Hyderabad. Now, I will little bit introduce about our speaker. I have to share this one. This is our speaker. Just a minute. Okay, so I have a short biography of our speaker. So Dr. A. Manmadha Cherry is presently working as assistant professor in the Department of Mechanical Engineering, ICFAI Tech School, IFHE University, Hyderabad. He has completed his PhD from the National Institute of Technology, Warangal, in additive manufacturing. He completed his master's engineering in production engineering from the University College of Engineering, Osmania University, and BTech degree from the Jawaharlal Nehru Technological University, Hyderabad. His research area interest include 3D printing, optimization technique, CAD/CAM design, and manufacturing of patient-specific implants. He has published more than 30 research papers in various referred international conferences and journals. He completed the R&D project for the Institution of Engineering. He received MEDIC 2018 Innovation Award from Indian Institute of Technology, Bombay. He has filed a patent on implant device for temporomandibular joint and method of production. He is the life member of Institute of Engineering and American Society of Mechanical Engineering. He is an editorial board member for the Journal of 3D Printing and Additive Manufacturing. He is working as a reviewer for many reputed journals like Journal of the Institution of Engineering India Series C, Springer, Journal of Mechanical Science and Technology, and Journal of Engineering in Medicine. He works with MNR Medical College and Hospital, Panya Institute of Dental Science and Research Center, Sunshine Hospital, Secunderabad, and Ozone Hospital, LB Nagar, for solving various critical cases through design and manufacturing. With this, I request to our speaker, Dr. M. Chairi sir, to deliver his lecture. Sir, now this stage is yours.
मैं रशिया का कर लेता हूँ तो वैसे ही हो जाएगा.
Thank you, sir. Unfortunately, actually, my webcam is not working. Sorry for this inconvenience. Shall I share my screen, sir?
Yeah, you can share it.
ठीक है, रशिया का काम कर रहा है.
I think you're seeing my screen.
Yeah, it is visible, sir.
Yeah, thank you, sir. Yeah, myself, Dr. A. Achari. Presently, I'm working as a assistant professor in Department of Mechanical Engineering, ICFA University, that is called ISPH University. Today, I'm going to deliver a topic on design and manufacturing of patient-specific implants using 3D printing. Okay, what is the 3D printing? Already, you know. Okay, so many speakers are delivered about the iteration of the 3D printing. Already, you know, if you wanted to make it just like a normal black and white photo, we are taking a normal printer. If you want to take the color printing, so we are using the color printer. How we can make a 3D model? How? Okay, for that we are using the 3D printing. Okay, same more. Okay, if you want to make a 3D model, we are using the 3D printing. Okay, that is a normal thing of the about the 3D printing. Actually, what is the definition of the 3D printing? Actually, the Terry Holler, he is given the definition in the 1980s. The 3D printing and rapid prototyping is a technology that produces the models and prototypes from the 3D CAD model or CT or MR scan data and data creating from the 3D object digital systems here. Okay, in this self, we can define. Okay, we can make a models with using the 3D CAD model or CT or MR scan model. Why we are using the CT or MR scan model here? Okay, to make some medical models. Okay, to make a medical model also, we are using the 3D printing and rapid prototyping. So that's why they are given the definition as like this one here. Okay, thereafter, the AICTE F42 committee, they are defined the additive manufacturing as a process of joining a materials to make an object layer by layer as opposite to the subtractive manufacturing process. These are the definition. Okay, from this definition, we can conclude, okay, with using the 3D printing, we can make a medical model. Okay, where we are using this 3D printing, which industry we are adopting this 3D printing now, you can see. Okay, this is a pie chart. This pie chart is given the TT holder. The TT holder reports annually. They are publishing a report based on the additive manufacturing progress in worldwide. Okay, from this, okay, we can observe the first one. Okay, industrial business machines, they are using this additive manufacturing technique. The second one, aerospace industry, they are using these techniques. Then the third one, the motor vehicle. In the automobile industry, they are using this 3D printing there. Next one, fourth one, almost all these consumer products and electronics and medical and dental. Okay, the fourth one is the medical industry. Okay, nowadays, the 3D printing models and additive manufacturing models are widely using in the 3D in the medical industry. Okay, here, same thing. This Holler, he is given the forecasting of the additive manufacturing process, how the progress is going on. Okay, this he's illustrated with using this iceberg mechanism here. Okay, this is the the stop portions. Okay, whatever the models are there, this already existed. Okay, now this is the upcoming models. Okay, the medical implants and custom processes. Okay, these are the upcoming objects with using this additive manufacturing technique. In the future, if we can get the human organs. Okay, we can get the smart and intelligent structures. Okay, in unimaginable applications purpose also we can use the 3D printing technologies. Okay, now this session is going to deliver a design and manufacturing of a customized implants. How we are going to manufacture the implants. But this is an upcoming and it is a new industry or a new application for this manufacturing industry. Okay, where we are using this medical models. Okay, and now with using this additive manufacturing technique, we can make a surgical planning models, we can make implants, we can make surgical guides and templates, we can manufacture with processes, we can develop a scaffolds. With using the additive manufacturing or 3D printing, already you know the additive manufacturing, 3D printing, rapid prototyping, solid free form fabrications, all are the synonyms. Okay. Okay, with using the 3D printing techniques, okay, we can make the surgical planning models. Why? How we are using the surgical planning models? Suppose, okay, you can see this is a, or these twins, they are born with attaching this head. But the doctors, they are going to conduct a surgery to split these two heads. So for that reason, first they are manufactured this or models. These models, they are manufactured with using the additive manufacture techniques with patient CT images. Then the doctor performed a mock surgery on these models. How we will make a plan, how we will do the surgery, that they are estimated based on these models. Okay, that is the surgical planning models. Next one, implants. Nowadays we are seeing, okay, so many doctors, they are implanting the knee joints and hip joints, or okay, so many various type of joints they are replacing. How they are manufacturing these joints here? This implant, this this is a knee joint, this is a hip joint. Okay, each patient having their own unique dimensions. Okay, one patient to the another patient, they, okay, there is no matching the dimensions. So that's why the patient specific unique implants are required nowadays. Then we can fit the implants properly. Then the patient sustain in future, in long life. So that's why nowadays we are concentrating on patient specific implants. For making this patient specific implants, these additive manufacture techniques nowadays we are using to develop these implants here. Next, okay, this next one, the surgical guided implant. Okay, these implants, how we are going to fix inside of the patient. For that, we require some templates, some guides. In our mechanical engineering also, we require some guides to make a hole. Similarly, here also, to fix these implants, okay, this is a hip implant here. This to fix this implant, we require some surgical guide to place the implant properly, to make a hole properly. For that purpose, okay, we are manufacturing the surgical guide with using the additive manufacturing techniques. Next is the prosthesis. Okay, the prosthesis is a replacement of the human part, the outside. The implant, okay, we are placing a model inside of the patient. That is called the implant. The prosthesis, just we are replacing the human anatomy with using these models. That is called the prosthesis. Nowadays, okay, a hand, okay, this prosthetic arm and prosthetic leg. Okay, so different type of prosthesis we are manufacturing with using the additive manufacturing techniques because of the unique dimensions of the patient. Next one is the scaffolds. To replace a bone, or to replace the human organ, or to replace the human anatomy, okay, we are replacing the scaffold. After some time, the bone will be grow inside of the porous structure. Then this object is going to decompose. Okay, that is called the biodegradable material they are using. This type of, okay, this type of structure is called the scaffolds. The scaffolds is uh, using to at increasing the cells growth inside of the object. And now you can see here, this is a 3D printed PLA scaffold, polylactic acid and hydroxyapatite scaffold. In this porous, in this small holes, after fixing this scaffold, in this holes, the tissues will be grow. Where the tissues is growing, automatically this scaffold will be decomposed gradually. These type of models nowadays we are using this additive manufacturing technique, or 3D printing technique here. Okay, even human organs also we are going to manufacturing, but that is coming under the bioprinting. So that's why I'm not keeping the application in the additive manufacturing techniques. Okay, in the future we can we can manufacture the human organs with using this bioprinting. So how we are going to manufacturing a patient specific implants? What data is required? Which software is required? Okay, that is we are going to discuss in this session here. Okay, here you can see this is a flow chart how we are going to manufacturing a models, medical models here. Okay, first, okay, we require the patient specific implants. Okay, just now we are seeing, okay, the implants, we require the patient specific implants. These hands, okay, we require the patient specific hands because different humans having the different their own dimensions. One patient to the other patient, we can't replace this type of joints, this type of prosthetic hands. So that's why here we require the patient specific models. For that, first we are taking the CT data equation here. The first initial step is the CT data equation. In this one, we are collecting the image from the patient. Then after whatever the images are there, okay, here this is the raw data. From that raw data, we are going to construct a CT image. Okay, that is we are saving as a DICOM file format. From the DICOM, we are creating the CAD model. This is a common steps for making the implants, to making a prosthesis, to making a surgical guide, to making a pre-plan surgical models. Thereafter, suppose you require only pre-surgical models. Just this CAD model, we are converting a STL file. Okay, then this STL file, we are developing a models with using the additive manufacturing machines. Then okay, we can these models we can use as a pre-planned surgical models. Okay? These pre-planned surgical models used to perform a surgery, and we can reduce the time of the surgery. Okay, we can reduce the blood loss of the surgery during the operation. That we can control with using these pre-surgical models here. Okay, suppose you require some implants or prosthetics. For that case, this STL model, we are converting a normal CAD model, and that we are doing some molding. If you want to make some joint, that joint you have to attach it. You want to make a hole like that. Okay, whatever the some CAD operations we are going to do. So for that, because this STL file, we are converting the CAD model. On that CAD model, we are doing some operation. Then we are creating the object. Okay, that object, okay, we are going to testing before going to implantation. So after testing, we are using for the implant. Okay, sometimes, okay, we have sometimes we require some optimization of the implant. So actually, the bone density is the different. Okay, the metal density is different. So we have to replace exact amount of the weight, whatever the bone is removing from the patient. So that's why, okay, we have to keep the same weight. Okay, how much amount of the bone is removing from the patient. For that, okay, we are doing some we are using some topology optimization. After optimization, we are going to manufacturing a model. That model we are using as a implanted processes. This is a general step to make a implant, to make a processes, to make a template, or to make a pre-planning surgical models. Now here we are going to discuss about step by step here. The first step is the medical scanning. So here what is doing here? The medical scanning, okay, we are collecting the patient data. Nowadays we are using the industrial CT scanners also. Okay, the industrial CT scanners is using to identify the material or the identify the blowholes inside. Okay, after casting. For that purpose, we are using the industrial CT scanners in the NDT testing. Okay, you can go each and every layer, you can test it. Well, like that, we are using the industrial CT scanner. Same, okay, these CT scanners we are using in the medical community to acquire the patient data. Suppose I require this bone, I require this nose, I require this lungs. All these things you can extract with using this CT scan. And this is the initial step to make an implant, to make a pre-planned surgical models. Here nowadays, okay, different type of CT or medical devices are available. The computer tomography. This computer tomography majorly using to extract the bony part here. The MRI images. These MRI images, okay, using extracting from the soft tissues. The ultrasounding images. So wherever the very soft tissues are there, on that we are using this ultrasounding imaging. Suppose to get the fetal data, for that case we are using this ultrasounding imaging. The cone beam computer tomography here. And majorly this cone beam computer tomography technique is using in the dental industry to extract the mandible image. Okay, this is a small size CT scanner. Here, okay, the X-ray beams are going to the cone shape. So that's why we are calling as a cone beam CT scanning. The computer tomography. You require the micron data. Okay, you require the micro size data. For that case, we are using the micro computer tomography. Next is this positron emission tomography. All these things, okay, so many different type of scanning techniques are using to extract the data from the patient. So that is the first step here. What is going on in the CT scanning here? So here, this is a technique to take the patient patient images. Okay, but the patient is lying on the bed. Now here, the X-ray tube, okay, is giving the X-ray beams. At the end, okay, the detector is there. The detector detects the X-ray beam. So when this X-ray beam is passing through the anatomy, passing through the patient, some energy will be lost. So whatever the energy is losing, based on that, we are going to construct the image. So for that, we are using so many algorithms to detect this X-ray or this CT images. Then majorly we are using the back projection algorithm we are using in the CT scanner. Okay, after doing the CT scanning, we are getting the images. Now you can see here. Now you can see here. Okay, I wanted to make a scanning here. The X-ray tube is rotating like this one, the helical fashion here, like this is rotating. Just same like our screw. Okay, from here to here we are getting. Okay, here also we are calling two successive points is called the pitch. Okay, this is called the slice thickness. Okay, when this one is both are merging, that is called the slice interval. Based on we are giving some values to make it to get the exact image from the in the CT scanner here. Okay, here okay, from when the X-ray tube is traveling from this distance to here, the number of images are collecting here. These images we are going to printing in the sheet. That sheet, okay, the radiologist is giving to the doctors. So wherever the defect region is there, okay, wherever the defect portion is there, the defect region, defected portion images, they are printing in the film. Okay, based on these 2D images, the doctors is going to diagnose to the patient. But to suppose you want to do medical models, you want to do people on surgical models, suppose you want to make some implants, you have to collect all the DICO images. Okay, suppose you require this head. So from here to here, normally the 0.625 mm slice thickness we can get in the CT images. Here we require this head. Almost at this head size is 15 centimeters. So I'm taking the 15 centimeter length is required. My slice thickness is 0.625. Now you can collect here 15 centimeter by 0.625 mm. How many images are coming? That images, okay, we are going to collect, and that images is using to make a CAD model, to make a implants. Okay, only these images are required for the doctors. For engineers, we require all the images. That images we are going to construct in the 3D model. Here in the DICO images is consisting of the 2.5D images. Already you know what is the 2.5D. Who is teaching the CAD subject, they know. Okay, the 2.5D dimensions means okay, that entire thickness having the same cross section. That is called the 2.5D images. That 2.5D images we are getting in the DICO images. Suppose you can see this X-ray beam, okay, this X-ray tube, okay, giving the X-ray beams. Okay, this region we can get the image. Here you can see this is the thickness. How much thickness we can define? Okay, that much thickness we can extract with using this detector. Okay, this is the detector with here. Here we are getting the 2.5D. Now here, how we are going to deliver this 2.5D image to 3D CAD model. Now you can see here. So here, this is called the voxel. Only we are having X and Y. That is called the only when we are having the X and Y dimension. That is called the pixel. Okay, you can see. Okay, those who are, when we are getting the images, we are getting the pixel. But in the CT images, we are getting the voxels. From the voxel, we are developing a CAD model here. Okay, now you can see in the voxel, we are adding the Z dimension and the thickness. This is a X, this is a Y, this is a Z. These voxels, we are arranging sequentially based on these coordinates. Then we are getting the object here. Suppose this is a total entire the volume. In the entire the volume, I require only this object here. To extract from the entire object to this one, we are applying some thresholding technique here. Here, however, the density we are applying in our mechanical components, here also we are applying some thresholding. Okay, in this, when we are applying the thresholding effect, we can get our required object. So whatever the region of interest is required, that region of interested voxels is going to match, and that matched value we can get. Okay. That is the principle of convert the dichromagic CAD model here. If how we are going to develop this dichromagic CAD model? Okay, here, so nowadays so many softwares are available in industry. Okay, a 3D slicer, a 3D doctor within medical design studio, mimics USA 3D, D2P, design to print, Cinema 4D, mesh mixture. These are the softwares nowadays we are using to develop a dichromagic STL file here. We can't get the CAD model. We are getting only STL file. Okay, with using this softwares here. Okay, now here, okay, in this one, the 3D slicer, the first one, it is an open source software. But with using this 3D slicer, we can extract the region of interest, and we can develop a CAD model. We can develop a STL file. Okay, in this software, so many modules are available here. These are the different modules. Okay, with using these different modules, we are going to extract the STL file here. How we are going to extract the STL file, now you can see in a small demo. Sorry. Sorry, don't mind. It is opening the 3D slicer software. I'm going to opening here. I'm giving a small demo to convert that diagram image to the STL file here. This is helpful to make a medical models in additive manufacturing technique. This 3D slicer software is an open source software you can download from the net and you can utilize yourself. In this 3D slicer software, the input is the diagram images. Okay, after getting the diagram images from the CT images, so from the CT scanning, okay, that images we are going to giving in this 3D slicer software here. Okay, this is a 3D slicer software. To make a medical model, the first we require the diagram images. Already we know. The first we are going to load the diagram data here. Suppose already this is there, so I'm going to import once again. Load, okay, import the diagram images. So where is the image over there that you have to select? Okay, here the diagram images are already available on my desktop. The diagram images I'm importing inside here. Now you can see here the images are importing inside of the 3D slicer software here. Now you can see here, this is the 512 by 512 size and 136 count here. That means this is the peak. Okay, this is the 512 by 512 matrix size here. The image, the 512 size of the pixels we can get. Okay, that is telling about the 512 by 512. This is the matrix size. Okay, next here 136 images are getting when we are performing the CT data CT scanning. So these images we are loading inside in this software here. Okay, these are the images. Now you can see here. Okay, I want to make a maxilla and mandible. So for that, okay, here I'm taking the CT scanning. This CT scan images you can see here. These are the different views we can see in this software. Okay, this is the top view to bottom, top to bottom. You can see here. This is the bottom of the chin. Now, okay, from the chin we are going to head here. Now you can see here. Okay, these are the teeth. And now the maxilla is coming now here. This is the orbitals. And this is the top portion. Similarly, here in this we can view from front to bottom, from front to back. Now you can see here. This is a back one. Okay, this is a spinal cord. This one. Okay, from back we are coming to the front now. Here you can see here. Okay, this is the mandible here. Similarly, in this one, we can get the side view from one left to right. Okay, this is the one side of the ear. Now we are going to from one side to another side, from left to right now here. Now you can see these are the teeth. This is the nose. This is another side of the ear. Like that, okay, we can import in these diagram images in the 3D slicer. These are the diagram images here. Now here I want to make a object here. My intention is, okay, I require only this maxilla and mandible portion only. I don't require this spinal cord. So I want to do surgery at this region. So I'm removing these images and I'm extracting this one, and this model we are going to save as a state file. Okay, that is required here. So how we are going to do these operations, now you can see in this small demo here. First I'm going for the volume rendering module here. Next, whatever the volume is there, I'm going to assign the volume. Okay, okay, how much crop is required? That for that purpose, I'm enabling this one. Next, display ROI. Okay, ROI means region of interest. What are the region of interest that you can do it here? Okay, this is the crop box here. How much volume is required that you can extract? Okay, that you can assign in this box here. Now here, okay, you can see here. This is okay. This is consisting with the soft tissues and muscles and bone. So here I require my region of interest is only bone. So for that, okay, first I'm going here and I'm selecting the whatever the region of interest is required that you can select in this software here. Suppose you require some liver, just you can assign this CT liver threshold value here. Suppose you require only articles, artitus, okay, that you can extract here. Suppose you require only this corner that you can select here. Suppose whatever the region of interest that you can see, default you can select with using this thresholding values here. Suppose you required only this CT air, okay, whatever the air you can if you wanted to extract air particles inside of the body, that you can extract here. Suppose you require some CT MIP. Suppose you require only some nerves, you require only some soft tissues, okay, fat, you require only bone. So whatever the region of interest, based on that you have to select the threshold values in this software with using this module here. So here, okay, if you require only cardiac, okay, that you can select here. So here my region of interest is required, my region of interest is bone. So that's why I'm choosing the CT bone here. Just I'm clicking the CT bone, because normally the implants we are placing instead of the bone. So that's why, okay, we are taking this bony information with using the CT images. Now you can see here, when I'm selecting the CT bone, now you can see the bony images. Okay, from the entire the soft tissue, you can extract the bony models here. Here you have to apply some local tissue values here to select the proper images. Now, okay, I'm selecting the proper threshold value with changing this cursor. Here we are giving the 164 images, so that's why it is taking some time to calculate all this information. So for that, okay, we require the high-end software here. So high-end system is required. Now you can see here, from the entire the soft tissue, I extracted only bony region here. So, but here a little bit something soft tissues are there here. So that also I'm removing with changing this value here. The first step, okay, here from the entire the tissues, okay, we are selected the bony part here. The second step, I require only these images from here to here I require here. So I don't require this region. So whatever the region is required, that region you have to fix it in this box. Okay? That is called the cropping here. How we are doing the cropping in the normally 2D image. Similarly, here also we can do the cropping in all the images when we are selecting this cropping tool here. Next, okay, I'm selecting this box within our required object here. So it is a little bit is taking some time because it is selecting all the 164 images. So that's why this time is taking to select this one. Now, okay, just you have to pick this one point and drag it When I'm selecting one here, but all these images is selecting automatically. Whatever the 164 images images are there, that all images automatically is going inside of this box. Here, okay, now, okay, when I'm seeing the top view, okay, it is looking good. But when I'm seeing the side view, okay, now you can see here, okay, this region is not required. Okay, so once again, okay, you have to go in a different region and you have to choose, you have to select proper crop value. Now, okay, I'm going in each and every layer, how it will be look. Okay, that is, I'm going to checking, and a little bit I'm going to adjusting this crop volume here. So I record only this region, so that's why I'm selecting only this region. I'm removing this region here from the entire city images. Now I'm selecting this region, okay, this view. Now, okay, here in this view it is good. I record only this region. Now, after selecting this one, now we are going for the crop value. Converts. Next, we are going for the crop volume module. Here we are choosing, okay, how much volume is required. Now that volume we are going to do the crop voluming here. Okay, to extract this crop volume, okay, different options are available here. Nearest neighbor, Windows, window into Syntax C, and linear and B-span. Compared to linear, B-span, we are getting the accurate model, so that's why I'm choosing the B-span. Then I'm going apply here. Now you can see when I'm clicking the apply, now you can see how it is going to extracting from this entire region to this region here. Now in each and every layer, it is going to the cropping. That the cropped images is collecting, and lastly it is giving the cropped images to us. So that is performing with using this software now. That is going inside of this software. So each and every image is going and collecting and doing the cropping. Okay, all this 164 layers is performing. That's why it is taking this much time to perform this operation here. For this, we require high-end softwares to perform this medical modeling, medical card modeling, and medical modeling. So this one here, each and every layer is going to calculating. Now you can see. So whatever the required image is there, that image we are getting from the total image. For this reason, we are using this crop volume. Next, go for the volume rendering. Remove this one, enable display ROI and volume. This is we are going to enabling. We don't require these boxes, so that's why we are removing that one. Next, we are going for the editor. In the editor, okay, we are going to apply a threshold value local here. Now my region of interest is bone. So here each human anatomy property we can assign with applying this bone. Okay, these density values. Already predefined density values are available in the software. So that I am selecting here. And now I'm choosing the bone. Okay, my region of interest is bone. So that's why I'm choosing this bone region. If you want, you can choose tissue, skin, blood, organ, okay, muscles, and what, okay, teeth and fat and gray matter, white matter, okay, whatever required you can extract with using this different tissue values. But my region of interest is here bone, so that's why I'm choosing the bone here. Then you have to apply the threshold value once again. Okay, whatever the value is selecting, that value image value we can assign with using the threshold values here. And now here I'm going to apply the threshold effect. Now you can see here when I'm choosing the threshold, okay, automatically this is okay, this bone is calculated here based on this threshold value. Now here once again you have to adjust locally. Okay, I require only this region now. Okay, you can see when I'm shifting here, this is the noisy images. I don't require this noise images. I require only this is my bone. Already we know this is my bone. Okay, this is the tissue. This is normal soft tissue. Okay, so that's why I'm choosing this one locally and I'm selecting properly. Then okay, I'm getting my bone here with adjusting this cursor here. Okay, after choosing this bone, now apply. Okay. Now go for the make model effect. Now we are going to making a 3D model here. Now you can choose here. Just I'm going to click a make model effect here and apply. That model I'm going to making with applying this one. Now you can see here. This is my bone. Okay, from okay in the earlierly the inside, okay, in the back side, the spinal cord, all this info, all these things are there here. Now from this to entire the object I removed, and lastly I got only this maxilla and mandible. This spinal cord is removed with using this crop value. Here so many modules are available here. Based upon our requirement we are going to do some operations, then lastly we are getting the object like this one. This is a simple technique to extract the CAD models with using the diagram images. Okay, this is an open source software. Okay, you can also use. Now here this CAD model I wanted to save here. Now I'm going to save. Okay, I require only bony portion, last portion only. So I'm removing this all these things. I'm selecting the bone. Here, which type of data is required? Are you require the poly data? Are you require the STL file? Are you require the .obj? Whatever the file format is required, that you can extract. The poly data, suppose you require the only outer shape. Okay, on that case, you can use the poly data. From the poly data, you can extract the surface and you can extract the solid, okay, with using various softwares, and you can write in your own code in your MATLAB. Okay, if you require the STL file, you can choose the STL file. If you require the OBJ, you can choose the OBJ. Suppose you require the color printer. So suppose okay, this human anatomy having the different portions, different anatomy. The different anatomy is requiring the different colors. For that case, you can use the OBJ. Here I'm extracting only STL. Just I'm clicking the STL. Where you have to save that path, you have to give here. I'm selecting this one in the desktop. Just choose then save in the desktop, this one. Now you can see it is saving on the desktop. So boom. Yep, boom. Now I'm opening. With 3D viewer, you can see the 3D model here. It consisting a lot of data, so that's why it is taking this much time. Now you can see, yeah, this is one. So when you are choosing the local threshold values, okay, you can get the exact model. Okay, some time is required. So within the short time, we are unable to process the exact model, but okay, we can get this one. Okay, the proper selection of the thresholding is very important in this software. If you are choosing the proper threshold value, you can get the exact model. Suppose you are not choosing proper threshold value, so you are getting uneven and irregular surface you are getting of the STL file. So that's why choosing of the threshold values are very important here. Suppose in the commercial software, in the Mimics, directly you can extract the bone. Okay, bone 226 values are automatically it is taking. But like this open source software, you have to define yourself. The commercial softwares are predefined algorithms are available. Based on that, automatically it will be give the information. It will be give the proper CAD model. So there is a difference between the commercial software to the open source softwares. The open source softwares, it is required some more experience. But the commercial softwares, okay, without the experience, you can extract the models. Okay, this is a STL file, yeah. Now you can see what is this data size. 28.6 MB. Now you can see this much while okay, this much size is taking for this simple object. Yeah, normally this medical models consisting of a lot of data. So this is about how to convert the diagram image to the STL. Do you have any doubts till now? You can ask in this one. Otherwise, we are going to go for the next topic. Thank you. Okay, here up to now, okay, we have developed only STL file, but STL already you know, okay, those who are working in the 3D printing field, so you know STL file is only default file. We can't do any editing. So if you wanted to make a hole, we can't do. So if you want to attach some attachments, you can't attach. Okay, it is only surface data, and it is no topology information. It is no, it is not having any mesh properties. It is having only tested value, tested surface. So if you want to do some implants, so another STL treatment softwares are required. First one, in the STL file also so many errors are there. Okay, who those who are teaching in the 3D printing subject, they know. Okay, in the rapid prototyping and technologies, Chua CK, he's given the best errors. Okay, the author is they define the proper definitions of the STL file errors on that book. So many STL file errors are there. That STL files you have to correct. First one, because this medical model we are converting the diagram images to the STL. So many errors will be occur. The errors you have to reduce. First one. Second one, if you wanted to make something, if you wanted to add some CAD modeling, if you wanted to do something Boolean operations, that STL file once again you have to convert as a solid model, because STL file are having only surface data. So once again this surface data to convert the solid file. Okay, and on that you can do some operation. These two operations are required after STL file conversion. That purpose we require some STL treatment softwares are required. Nowadays, okay, Magix, Thematic, okay, that is the commercialized softwares are available to manipulate the STL file, to correct the errors in the STL file. All these things you can do. There are these magic is using to correct the STL file errors. Thematic, we can do some Boolean operations. We can make some CAD modeling and the STL file. Okay, these are the commercial softwares. Nowadays, so many softwares are also available. Open source softwares are also available to do this STL file errors, to do Boolean operations on the STL file, to convert the STL file to the 3D CAD model. Okay? So many softwares are available. After doing this processing, then that model, once again, we are going to the AM softwares. Already, you know, okay, directly STL file, we are not importing to the machine. That STL file, okay, we are converting as a slices information. That slice information we are sending to the machine. To convert the slicing, we require one more AM softwares are required. Then this file we are sending to the machine. Here already we know up to this one you will learn. Okay, this is some information is required for delivering this. It is taking so much time. So in this session, I am unable to discuss all these things here. Next year, we are going to discuss about how we are going to do utilizing this 3D CAD model, how we are going to utilizing this STL file, how we are going to do the preparing surgical models, how we are going to do implants. Okay, some case. Okay, we are discussing with using some case studies. That is now I'm going to discuss in this presentation. So directly from the STL file, okay, directly we can't do the implants. Some softwares are required, some Boolean operations is required, some STL treatments, we have to reduce their risk. All these things we require. So that's why, okay, I'm giving this slide here. Directly, don't think directly STL2 we can manufacturing a patient specific implant. Some treatment is required from here. Okay, the whatever we are perform the case studies. Okay, that is, okay, the major I'm going to deliver for you here. Okay, this is a small case study. Okay, here this patient met the accident. Here, okay, this total, you can see the total entire teeth are collapsed here. Okay, no teeth are there, but the inside there is the lower jaw having the teeth here. So we have to reconstruct the teeth on the upper side with using this inclination of this lower teeth. So here, okay, suppose 2-3 teeth are there, easily we can identify, okay, what is the inclination, what is the angulation. So okay, here there is no teeth on the upper jaw, so that's why some difficulty is there. So that's why we are using the 3D printing technologies in this case here. So first we are taking the CT or DICO images. Here this is the dental model. For this dental model, they are using the CBCT images. Actually, in the CBCT images, we are getting uneven surfaces, and okay, we are getting a lot of uneven objects here. You can see that a lot of scatters you can observe here. All these things, okay, we have to remove. Okay, so for that we are using some smoothing algorithm. How we have to extract the smooth model with using the noise data in the CAD model. Okay, how we are, that is, we are written in one algorithm. Okay, based on that algorithm, okay, we are removed this noisy data, and lastly we got the smooth STL file with using this nasty data. Okay, we are publishing one paper with using all these algorithms and how we are going to perform this case study. Now, based upon the bottom teeth angulation, we are designed a implants. Okay, how we have to fix the implants. That is, we are assumed based on the bottom teeth. Then we are placed just like a circular rod on the upper maxilla. Then these teeth, the artificial teeth, we are fixed to the CAD model. Then with this implants and this maxilla, we are done the Boolean operation. Then we made a single object. This object we are using to make a additive manufacturing model here. Now you can see. Now, with using this additive manufacturing model, we are preparing one template how we have to make a holes, because here this is having a different angle. If we have to make a this type of angle hole, then we can fix proper implants. Otherwise, that implants will not will not coincide to the lower teeth. So that's why, okay, this because of this inclination, because of this angulation, okay, we made
Excuse me, sir. Sorry for interrupting. Your voice is somewhat low. Can you please make it somewhat more?
Okay, sir. Okay, just a moment. Is it okay, sir, now? Hello, sir.
Yeah,
Is it okay now?
Yeah, but it is low, sir. Means not too low, not too high, but it should be. It should
Medium.
be.
Okay.
Yeah. Now it is.
Okay, I will speak loud, sir. Okay. Okay, now here, with using this additive manufacturing model, we are preparing one template here. Okay. This template is using to make a holes on the maxillary portion. Okay, just how we are using that fixture, okay, jig, okay, how we are using the jigs and fixtures in our mechanical community. Okay, here for the similarly, we are prepared this template to make a hole inside of the patient, okay, to make a inclined holes, whatever the angulation required, that angulation we are getting with using this templates here. Okay, now this one we are placing inside of the patient. Okay, based on this template, okay, the doctors are performed a surgery and the doctors are first made a holes, then they are fixing the implant. Okay, for this surgery, okay, here we are designed the implants artificially. We are created the implants, and this fixed the artificially created implants we made a additive manufacturing model. With using this additive manufacturing model, we are prepared a template. Based on this template, the doctors are performed a surgery. Okay, this is our application here. So next one. Okay, nowadays, okay, the oral cancer is a very big issue in our India. Okay, now you can see here, almost all the oral cancer, the lip and oral cancer. Okay, from 2012 to 2018, the percentage of increased here, the percentage growth is increased. So we have to do the oral cancer surgery perfectly, then we can save the lives before going to the perform the surgery. So that's why here we are performing a small case study here. Okay, we are planning to make a titanium implant with using additive manufacturing in this case study, but unfortunately due to this ethical issues, we are not placed inside of the patient, but we are designed and manufactured. How we are designed and manufactured the implant with using this 3D printing techniques, now you can see in this case study. Here, now you can see here, this is the cancerous bone here. Okay, these are the different views. Okay, here in this view here, this one in this view here. Okay, these cancerous bone, first we have to identify. Then wherever the cancerous bone is there, that cancerous bone we have to remove. Okay, where we are removing this bone, we have to replace the artificial implant. Then the patient will be sustained. Okay, that is the surgical procedure in the medical community. So for this reason here, first we are prepared the CAD model. With using this CAD model, we are prepared the additive manufacturing model. This is with this one we made with using the FDM printer. Now here, okay, here this is the FDM printer. But actually, in this case, if we have to remove this bone, in this portion we have to artificially create the bony part with using the implants. That is my idea here. So now, okay, this portion we are removed in the CAD model. Then how whatever the bone is there, that is we are estimated with using this physical model. Then okay, here in our mimic software we are having some option, we can make a mirror. So here after removing this bony portion, we have to replace the bone here with using our implant. Okay, for this reason, okay, this side bone we are mirror this side. Okay, this with using this part we are going to make an implant. Okay, that is the idea here. So is it fixing or not properly? Okay, for that checking purpose, okay, we are using this additive manufacturing models here. whether it is fixing properly or not. For that fitment checking purpose, we made this 3D printed models here. Then after this CAD model, we are going to use for the further processing to design an implant. Now here, actually, here one nerve is passing from this region to this region. Okay, that is called the inferior alveolar nerve. IA nerve is required here. Okay, that nerve is passing from this to this one. With using that nerve, we can open and close our mandible. Otherwise, okay, if the nerve is not there, we can't open, we can't close. So here one nerve should be passed with using this implant. That is the instruction is given by the doctor. So that's why we made a hollow portion. Okay, instead of the solid one, we made a hollow portion here. Okay, now with using this hollow portion, once again, we require some hollow portion. Okay, in this one, we are creating artificially bone inside. So that is the idea. So that's why we made some holes here. And here inside some hollow portion is there. Okay, here we are placing a IAN now. Then okay, he can able to open his mouth freely. So for this reason, we made a hollow portion inside to reduce the weight, to increasing the bones inside. For that purpose, we made these holes here. Then this hollow portion we are going to replace with using the replacing in the cancerous region. So okay, here is it fitting or not? All these things we are tested in the physical and virtual model. Then okay, this model we are going to do an implant here. So okay, this is the curve. Okay, this is a high sharp corners out there here. Okay, we have to reduce the sharpness. So that's why we are use some smoothing algorithms to do the smoothing on the surfaces here. Okay, then after using the smoothing algorithms, okay, we got this shape here. This shape okay, we are using to make to make a implant. Here, this portion, okay, already this portion we are fixing here. But how we have to fix here? Some okay, here some plates are required to fix. Some screws are required to fix this implant. So because of that reason, okay, we made these plates here. Exactly this plate, it is aligning on the condylar region here. This is condylar, here, this one. And okay, here this is the ramus region. Here in this ramus region also we have to fix the plate. Now you can see this is an uneven surface. It is a or some curved portion is there. Exactly, it should be fit on the surface here. So whatever the dimensions are there, or whatever the curvilinear is there, based on that, okay, we are design these plates. And okay, this one, okay, this is a CAD model. From this CAD model, we are prepared the 3D printed model. Is it fitting or not? Okay, we are tested on the physical model here. Now here. Now exactly it is fitting here. It is fitting here. We can place the screws here and here and here and here. So the okay, that fitment we are achieved here. Okay, this is the plastic model we made with using this STL file. With using the same STL file, we made the titanium implant with using the SLM process here. It is an additive manufactured implant here. This implant we are going to fix the patient, but this implant is heavy. After manufacturing, we observed this is very heavy compared to the bone. So that's why once again, what we did here, this design we are optimized with the topology optimization here. We are reduced the weight. We are okay. We made some spore structure here. Because of the spore structures, the bone will be grow easily, and because of this hollow portion, we can remove the weight. That we are performed with using this topology optimization here. After topology optimized object, we made this object here. Okay, this is the implant. This implant we are going to fix here, but it is taken nearly 4 months to design from this stage to this stage. But within these 4 months, now the cancer is increased from normal this region to from this region to this region. So that's why okay, we are unable to place the implant inside of the patient, and due to some ethical clearance, okay, we are unable to place this implant, but we are designed and manufactured with using this additive manufacturing techniques here. But to get the symmetry of the patient, okay, we use this 3D printed model as a pre-surgical planning purpose. And now here, based on our CAD model, we are identified we are identified the cancerous region, and where we have to cut how much amount of bone will how much amount of bone should be removed from this mandible, that is we are estimated with using this CAD model, and we are given the dimension to the surgeons. Okay, based on this area, based on these dimensions, okay, the doctors are got the idea how much amount of the tissue cancerous and how much amount of the tissue will be removed from this mandible. Okay, they got some idea based on these virtual models. Then okay, here how much amount of the bone is we are planned in our CAD model for the removing purpose. The same okay shape okay they are removed from the mandible. Here now you can see this is actually cancerous bone here, but this is prolonged from this region to this region and this region. So here, whatever the cancerous bone is there, that it should be removed from the bone. Otherwise, this cancer is increasing after completing the surgery. So when we are, what happens, sir? Anything wrong? Anything wrong, sir? Hello, sir? Hello?
No issue, sir.
Oh, okay, sorry. Okay. Here, okay, we are going to removing here. Okay. Because of this CAD models, we are identified the cancerous bone region, and then okay here whatever we are manufacture this 3D printed model here. This 3D printed model is using as a surgical aid for the pre-planning surgery purpose. Okay, here okay, after removing this bone, we are placed here one titanium plate here. Okay, when we are using this model for the pre-planning surgery, here we got the exact curvature to bend the plate here. Okay, this is actually this plate having normal straight plate. When we are purchasing from the vendor, it is having a straight plate. This straight plate we are okay, these doctors are okay modified according to the patient dimensions here. Okay, according to the patient dimensions they have to modify here, but the patient dimensions we can't get. So okay, because of the 3D printed model, okay, they are achieved. Okay, how we have to how we are going to bend the plate here. Because of this 3D printed model, okay, they are got this curvature, they got this bending. This plate they are bended based on this patient mandible here. Then this plate they are implanted in the patient, because this is a medical certified plate here. They can implant in the patient here. When we are using this curvilinear portion, okay, after completing the surgery, he can get the symmetric shape. Okay, if suppose we are not using this curvilinear portion, or they are having uneven shape. So to get the symmetric shape of the patient, okay, in this surgery they are using the 3D printed models here. And now this this plate, this is a stainless steel 316L. With this plate, they are placed inside of the patient here. Now you can see here. Okay, this curvilinear portion we achieved with using our 3D printed model here. Okay, this is a removed tissue here. After placing here, okay, they are stitching here. Then you can see here in the X-ray image, you can see here. This this curvilinear portion. Okay, this we are got with using this 3D printed model. This is called the pre-surgical planning here. Okay, because of this pre-planning surgery, okay, because of this bending before going to the surgery, they got perfect shape and they reduce the time. Okay, they can got idea where we have to fix, how we have to fix. Okay, that they are achieved. Okay, in this 3D printed models. The second one, okay, here this bone, okay, this cancerous bone, okay, so many patients are suffering. Okay, when we are placing this implant, okay, now he cannot eat properly because here there is a hollow portion, so he can't sustain properly. So when we are placing inside of this hollow portion something, okay, suppose in the bone is growing from here to here, now he can sustain. Actually after 10 years the bone is growing from here to here, the doctors are telling like that, but it's taking long time. So here we are going to we are developing one device to develop a bone within 6 months. Okay, for that, okay, with using some device. Okay, that we are developing one distractor with using this 3D printed model. Okay, in the second case here. So whatever the defects are there, the defects we are going to fulfill in the next case here. Now you can see there is a same thing. This is also cancerous bone. Okay, that cancerous bone you can see here in this one here. Those who are eating the tobacco, the people they are getting this type of infections here. This is also one type of the cancerous here. Now here you can see this is the hollow portion. We have to remove bone from here to here. Then okay, we can save the life. So when we are removing from here to here, now he can't eat, he can't sustain properly. So in this case, we are going to prepare a one distractor with using this 3D printed model here. Now this is a bone. Okay, this is a cancerous bone. This cancerous bone we have to fulfill with using our distractor. Here, that one treatment planning is there in the medical community, that distraction osteogenesis. When we are removing the bone, we are stitching the bone within small gap. Within this gap, the bone will be grow. Okay, that is a bone property. Because of that property, okay, we can extend the bone. Okay, that method okay, we are used in this technique, in this surgery here. Now this is my plan. Okay, this is the doctor's plan here. First, they are going to remove here. Okay, whatever the cancerous bone is there, that cancerous bone they are removing. Then, okay, this also they are removing the. Okay, they are going to cut here at this region and at this region. This cut. Okay, this cutting portion they are not. They are stitching. They are not completely. They are cutting here. They are stitching the bone from here to here. When this stitching is going to from this region, this area, this point to this point, maybe the bone will be cured inside here. Then this bone is okay. Now okay, this bone is stitching from this here to here. Okay, when this bone is stitching, okay, here here we can get some hollow space. In this hollow space, the bone will be grow. For 1 week, 1 mm bone will be grown inside. Okay, because of that property, we can extend the bone. And now here, this bone is going to here. Then they can, then he can get the proper shape, and the bone will be grow within the short period. Now the patient sustain properly. This is the idea. For that we require some template. Okay, how for moving this bone and to guide the direction of this bone. Okay, all these things. Okay, we require some direction, some template is required here. For that one, we prepared a this model here, this distractor here. Based on the CAD model, we have prepared the CAD distractor. Again, how where we have to place, how much length is required, how much angulation is required. All these things we are getting with using these CAD models. Okay, this is the different views. Now, based on these dimensions, okay, based on this angulation, okay, all this based on this dimensional information, we are prepared the distractor with using this 3D printed model here. Okay. This CAD model, we are prepared the 3D printed model. With using the 3D printed model, we are going to develop a distractor to guide this bone. Okay. First, they are removing this bone. Okay, then they are cutting this bone. This bone is going to extending. Okay, then the bone will be come he at this region. This bone is coming to this region. Then okay, the bone this total mandible will be fulfilled inside. So for that, okay, we are prepared this distractor here. This one. Okay, this is the 31L stainless steel. This is the medically certified plates. Okay, these plates we are purchased from the outside. And okay, this is a prepared with using our CAD dimensions, okay, with using these 3D printed models here. Here now, okay, this bottom plate is using to support the mandible here. This one here, we require some guide. We require some bone movement. Okay, this is the guide. Okay, for that reason we are using this one. To movement of the bone purpose, we are using this screw here. Okay, when we are moving, okay, when we are rotating here, this will be moved from here to here like this one. How is moving? Based on this lead screw here. Okay, this is based on this guide. Okay, it will be moved here. Okay, this is the idea. Okay, based on this idea, okay, we are prepared this implant here, this one. Now here, okay, we have performed a mock surgery. Is it properly moving or not on the 3D printed model here? Now this is the cancerous bone. This cancerous bone were removed. Now they are going to make a cut here. Okay, based on this cut, okay, this okay, we got these two parts. These two parts is going to move along this distractor to fulfill the this region at the mandible region. Now here, okay, this one, this bottom one, this one, this guide we are fixing to the mandible region here. Now here, this one, okay, this where we are going to cut here, that cutted parts we are fixing on the lead screw here. This is on the screw here. When we are rotating this one, it is moving along this screw. Then, okay, the bone is going to move from here to here. Now you can see this bone is not cutting the perpendicular. We are cutting the 45 degrees. So the bone will be grow like this one. When this bone is extending, the bone will be grow in this region. Okay, per 1 week it is going to 1 mm, above 1 mm is going, okay, growing. So because of this property, we can increasing the bone in this region. So for this region, okay, for this planning, we are prepare this implant here. Now you can see, okay, how it is moving. All this mock surgery, okay, pre-planning surgery performed on the 3D printed model. Okay, with using the 3D printed model, with using the CAD model, we are designed and manufactured this implant. And the doctors have performed the surgery. Now you can see here, this is a cancerous bone. The cancerous bone is removed here. Then after they are separated this region at the left side, then the right side. These two separated bony regions is fixed to this implant here. Now you can see here, this region is fixing to the rhombus region here. This is a condylar region, and this, okay, whatever the cutted portion is there, that cutted portion is fixing to this implant here. Now, okay, this part we can rotate on the implant here. Okay, the left side, this is the right side, same. Okay, and after 6 months, okay, now it is after 3 to 4 months, okay, it is going to from here to here, this bone. Similarly, this bone is moving to here to here. Then, okay, this is having the curvilinear portion. Because of the curvilinear portion, okay, we are getting the curvilinear shape instead of the mandible. And okay, we can increasing the bone growth with using this distractor. We can get the shape, symmetric shape. Okay, we can increasing the bone naturally. So then the patient sustain properly. Because of this reason, we are developed this implant here. Now you can see after fixing this one, okay, in the patient, this is the X-ray image here. This is your model. For this model we are developed for the oral cancer patients. Next one, okay, in my thesis, I developed a temporomandibular joint with using the 3D printing technology. Okay, we are claimed a patent. Okay, it is in the final stage. We have submitted the review. We are examination to this examination report also in the last week. What is the temporomandibular joint here? Where the maxilla and mandible is moving, and that region that region is called the temporomandibular joint here. Okay, here some people they are having the birth defect. Because of the birth defect, okay, they can't unable to open her mouth and his mouth. Okay, now this mandible region and this maxilla region both is going to fusing here. Here there is no movement here, so that's why he or she cannot open her mouth. They can't talk. They can't eat. That is a one type of birth defect here. Okay, when we are placing the TMJ joint, then they can open her mouth. They can speak. They can eat. Here, this temporomandibular joint, okay, nowadays the milling process, different processes are available in the India. If we are designed and manufactured with the 3D printed and patient-specific implants. Now you can see this is a CAD model. Okay, this is the temporomandibular joint. Okay, this is the mandible. This is the maxilla here. Okay, when it is having this joint, now they can open. Suppose okay, this maxilla and mandible is going to fusing here. Now he or she cannot open mouth. So this defect is there for this case. So now okay, we are going to replace a TMJ joint here in this case study. Now okay, with using this CAD model, okay, we are ADA IT manufacturing models. This is IT manufacturing models. Now you can see here there is a no bone growth from the birth, so that's why the maxilla is grown and the mandible is not growing. So that's why okay, she got the uneven shape. Now you can see how is there how she. So this side growth is there, this side no growth is there. So that's why the teeth are also not aligning properly. After placing the TMJ joint, she can't eat because of uneven teeth alignment. So that's why we are going to correct a proper teeth alignment. Then we can replace a TMJ joint. Then she can eat, she can speak properly. So that's why first we are going to correct a unsymmetrical shape. Okay, this whatever the gap is there, that gap we have to fulfill from this region to this region. Then we can place a TMJ joint. Now here the mandible destruction osteogenesis technique is there. Already we are discussed here. Okay, this bone we are going to cut here. Then okay, we are placing one distractor. When we are rotating this distractor per 1 week per 1 mm, the bone will be grow automatically. That is the technique. Okay, because of this technique, we are going to enlarge the bone one side, because here the one side the bone growth is good, but another side the bone growth is not good. So when we are extending the bone growth at this region, then she can get the symmetric shape, then she got the alignment of the teeth. So here that we are performed with using this IT manufacturing technique. Okay, that for that reason we are used this IT manufacturing models as a pre-planning surgical models. Here this is the distractor. This distractor we are placed. Okay, now here in this case, okay, this mandible we are going to cut here at this region and at this region and left and right side. Now one side of the distractor we are placing here, and the side of the distractor we are placing to this one region. Then we are going to extend. Okay, then we can extending with using this knob. Okay, this is already we know already. This is a lead screw. Here the nut and bolt mechanism is there here. Here, how much elongation is required here? That is the major thing here. Because how much elongation is required this side and this side, because this side the proper growth is there, this side there is a no growth. So that's why how much elongation is required left side and right side, that we are calculated based on this IT manufacturing models. Based on this dimensions, we are performing the doctors are performing a surgery with using this distractor here, this one. Now the distractors are placed inside of the patient. Now you can see here, this is okay, one side of the distractor is placed one side, another side of the distractor is placed in the other side of the mandible. Then okay, this knob is coming to the outside here. Now you can see here this one, and when we are rotating this knob, then the bone will be grow inside. Okay, like that, okay, we are extended the bone inside to get the symmetry shape of the patient. Now you can see after 6 months, she got the perfect alignment and she got the symmetric shape here. But that performed by the surgeons with using this detector, and the surgery was planned with using the 3D printed models. And now you can see this is a pre-surgical photo, this is a post-surgical photos. Now this mandible is moving from this to here. Now you can see how is she now here, how the teeth are aligned here. That is achieved with using the 3D printed models here, with using the pre-planning surgical models. Yeah, after 6 months, okay, once again we taken the CD images. Okay, because of this destructor, we got the scatters, we got the artifacts inside. This artifact and scatters images we are purified and developed with the CAD model with using some smoothing algorithms, all these things. Then, okay, this CAD model is using to place a TMJ joint at this region. Okay, this is a TMJ joint where the maxilla and where the mandible is moving. Okay, at that region, okay, that is called the TMJ joint here. Now you can see here. Now to get the TMJ joint, first we are prepare the CAD model of the mandible, and here this is the healthy tissue. This is a fused tissue here. Okay, with using this healthy tissue, we prepare the TMJ joint. Okay, this is a condylar portion. This condylar portion, we are whatever the dimensions are there. Okay, based on this dimension, we have prepared the TMJ joint here. Okay, now we are identified how much length is there, this side and this side. Okay, how much variation is there. Based on the variation of the dimensions, we are going to place a implant. That is identified based on this CAD models, CAD model dimensions. Now, okay, we are going to prepare a TMJ joint at the fused TMJ joint here. Okay, this side is good. This side is not good here. Here we are going to place a TMJ joint at this region. Now here, based on this corner portion, okay, we are mirrored this side and we are achieved here. Okay, how much elongation, how much length of the region is required, that we are identified based on these dimensions. Okay, that one we are extracted the mirror tool. And here in this case, okay, now you can see in the bone having the hollow portion. When we are going to manufacture this hollow portions with using the powder bed processes, maybe some particles will be come inside. After placing this implant, okay, the powder particles is moving inside the blood, and maybe that is harmful to the patient. So that's why we are taking the outer shell of the condylar portion here. Only we are taking the polylines. Based on the polylines, we are prepared a solid model with using MATLAB here. Now you can see only we are taking the outer shell. From the outer shell, we are prepared the CAD models. Okay, then okay, this is the condylar portion. For this this condylar portion we are going to fix here. So how we are going to fix here? Okay, for this for that purpose, we are attached one plate. Okay, based on these dimensions, where we have to fix the holes, all these things we are achieved in this here with measuring these dimensions here. Based on the dimensions, we have prepared the plate. This is a CAD model, this is a prototype model here. Okay, this is the condylar implant here. Next, we are this condylar implant should be moved some part. Okay, for that case, okay, we are taking the fossa component here. Okay, already this is a healthy tissue fossa component. That healthy tissue fossa component we are mirrored this side, and based on the healthy tissue fossa component, we are prepared the fossa component. This fossa component we are going to manufacture with the plastic model, and this condylar portion we are going to manufacture the metal implants. Then okay, we can avoid the friction when we are placing the implant here. That is the plan here. Then here the next one we require the zygomatic arch. Okay, this is the condylar implant we can place here. This where we can fix the fossa component to rotate this condylar component here. So for that reason we are prepared the zygomatic arch. So zygomatic arch, okay, this one, okay, wherever the this is called the zygomatic arch. Based on the zygomatic arch dimensions, we can prepare a implant. For that, okay, we are taking the XYZ coordinates with using the CMM. Based on the XYZ coordinates on the surface of this one, okay, we are prepared here one implant here, this one. Exactly the surface is fixing on this zygomatic arch. Okay, now you can see this is an uneven shape. This is not even, and the dimensions also different. Okay, for that, okay, we are taking the XYZ coordinates. Based on the XYZ coordinates, we are preparing the zygomatic arch. This one exact fixing to here. Now this one is moving the inside here, inside. Okay, here on the bottom of this zygomatic arch plate, we are fixing this one. And now you can see how we are going to fix this TMJ joint. This is a zygomatic arch. This zygomatic arch implant we are placing in the zygomatic arch. The fossa component we are going to fix with using this zygomatic arch. The condylar component we are fixing on the mandible. Now these three things, okay, we can see here. Okay, this red parts we are going to manufacture the metal parts. This one we are going to manufacture a plastic part. Okay, these three things we can, okay, this one we are going to fusing with using some techniques. Then we can achieve the implant here. This is the plan here. When we are placing this plastic, we can avoid the friction, and we are going to make a mirror finishing on the condylar portion to reduce the wear. All those things we are planned, we are designed based on this CT images, based on these CAD models with using the additive manufacture techniques. Now here, when we are fusing this plastic to metal, okay, how much strength it can sustain. That is, we are calculated with using this experimental setup, and lastly we are achieved, okay, 33.6 kg it can resist. Okay, then we are identify the impact tester. So we are conduct the impact test and the fusing. Then okay, we are prepare the metal implants with using the SLM machine, DMLS machine here, with using this machine. Now we can see these are the titanium implants. Okay, this is the zygomatic arch. Now this is exactly fixing to the zygomatic arch of the patient. Okay, at this bottom of region we can fix the fossa component. Okay, on the fossa component it is rotating. Okay, that's why we are prepare the mirror finished component here. Now this one we are preparing on the mandible. Okay, now okay, here this one fixing the zygomatic arch, this one fixing that mandible with using the screws. All these things, okay, we are manufactured with using additive manufacturing technique. Then okay, this is the our TMJ joint here. Like this we are prepared here. Is it fitting properly or not? That is tested with using our additive manufacturing model. Okay, we are perform the mock surgery, how it is rotating, where we have to fix, is it fitting properly or not. All these things, okay, we achieved okay, with using this mock surgery on the plastic models here. Then okay, based on the mock surgery, the doctors are going to perform a surgery in the operation theater. Now here, okay, how we are going to fix these implants. For that purpose, we require some template. If we are having the proper template, we can fix easily. Okay, then the implant will be fixed properly. So for that, okay, we are prepared here one template. Okay, this is the template where we have to fix the zygomatic arch, where we have to fix the condylar portion, where we have to make a holes. All these things we can achieve with using the patient specific guide. With using this patient specific guide, we are going to make a hole inside of the patient to fix the implants. For that, okay, we are prepared this patient specific guide here. Then okay, they perform the surgery. Okay, this is the TMJ joint. This TMJ joint was fused here. The fused TMJ joint, okay, they are separated. Then she's opening her mouth. Okay, then they are fixed the implants here. Okay, this implant, okay, with using this guide, they are media holes. Okay, based on these holes, they are fix the implants on the zygomatic arch and the condylar portion here, on the mandible region. Now you can see this is the metal implants here. Okay, here when in the radiography we can't get the plastic component. That's why we are unable to see the plastic component here. This is the metal components here. Okay, this surgery performed nearly 2 years back here. Okay, now okay, after 2 years completed, okay, we are studied how the tissues are growing, how the implants are placing inside. Now you can see here the tissues are grown on the implant here. Now you can see here, because of the rubbing of this condylar portion, some small amount of wear observed on this one here. Because always this mandible is moving up and down. Because of that one here, okay, there is no bone growth. So here the tissues are grown here properly. So now it is safe. That is, we are concluded with using this test. Now you can see after performing the surgery, now she is opening her mouth up to 3 centimeters. Now she is able to open her mouth and up and down easily. Okay, this is a case study. This is where implanted titanium implants. That implants are manufactured with using additive manufacturing techniques. Still now we are placed nearly 12 TMJ joints in the various case studies. Now here, one more interesting case study. Okay, this one. Okay, here we are made a facial correction with using the 3D printing techniques. Here now you can see this is this patient met the accident. Because of the accident, okay, the bone is grown properly, and the bone is growing different way, and after performing the surgery, okay, they have got the unsymmetric shape. Okay, now okay, we have to make a symmetric shape of this patient. Okay, for that case, we are using the 3D printing technology. In this case, okay, we have prepared the CAD model based on the patient CT images. Now you can see okay, after performing the surgery, the bone is got that damaged here. So there is no proper shape. Now there is no symmetry. Because of this unsymmetry, he got the unsymmetric shape. When we are filling something here, then he got the proper shape. He got the symmetric. So that we are perform the surgery with using this plastic implants. That implants are manufactured with using the 3D printing techniques. How we made the implants, now you can see here. Okay, this is a mandible. This mandible we are split it in the two regions. Okay, now this is a left side, this is a right side. Okay, now we are going to mirror the object, this one to this one here. Now you can see here, this one is mirrored to this one here. This is this amount when we are keeping inside of the patient. Now he got the symmetric. Now you can see here there is no symmetry. Okay, now this portion is inside to the normal symmetry. So that's why, okay, when we are placing this region to the patient, now he got the symmetry. So that, okay, how much amount of the region is required, that region we are extracted with using the Boolean operation, with using the mirror operation here. Now this one we are going to place inside of the patient, but it is not uniform. Okay, now this, okay, this is maybe a STL file. This is STL file to where convert the CAD model, and now here okay, we are made a smooth one here and here. Because if we are keeping like this one directly, when the patient is touching to his face, it is not good, and some uneven shape coming outside. So that's why we are going to make a smooth outside here. Okay, that's why we remove the material here. And here, where we have to fix the implant here we require some curvilinear portion. If we are placing a curvilinear portion, this curvilinear portion is attaching to the mandible, then the implant get the higher strength. So that's why we are prepare this curvilinear portion, this portion exactly fitting to here. Then okay, we are going to fix your teeth here, because when we are fixing the teeth outside, maybe it is damaged, maybe it will be damaged when he falling down like that. So that's why, okay, this teeth, okay, the implants are also fixing here. This implant, this CAD, okay, this implant is going to fix at this region. At this region exactly. This is a plan here. Okay, this implant designed here with using the diagram images of the patient. There is a patient specific implant here. Okay, here this implant is not bearing any load. We require only aesthetic view. So that's why this implant we manufactured with using the plastic component here. There is a biocompatible plastic component. This implant is manufactured in Singapore. Okay, now this one is fitted here. Is it fitting properly or not? How it is fitting? That is, we are tested with using the 3D printed models. Then we are placed inside of the patient here. The screws is fixing here and in the bottom region also. Now you can see this is the our manufactured implant here. Now you can see how his shape now. How this is the before surgery, this is the after surgery. Now you can see here. He got the symmetric shape when we are placing this implant. This implant is designed and manufactured with using the 3D printing technologies, with using the CT images. Okay, next here, the same guy having the problem, he is unable to see properly, because now you can see here. Okay, here the orbital ball is coming down at this region because of the fracture. Oh, this is we are taking the ethical clearance because this, okay, we are placing an implant inside of the eye. So that's why we are taking the ethical clearance. Then we are performed the surgery. Okay, we are publishing one paper with using this case study. You can see. Okay, now here, okay, when the two orbitals are lying on the line, we can get the proper image. Suppose the orbitals are not having proper, okay, the orbitals are not having in linear, then we cannot get proper image. Okay, this is the functioning of the eyes. So now here you can see here, because of this fracture here, this ball is having proper alignment, but this ball is coming the down. So there is no alignment for the left eye to the right eye. So that's why he is unable to see properly. He's getting two images in a different way. So that's why we are going to place the implant inside of the orbital. Then okay, then we can get the linear alignment of the eye orbitals. So that is the plan in this case study. Now already okay, they are using these plates, but okay, sometimes these plates are going to failure, and sometimes they are getting itching. Okay, and it is not good. They are not suggesting the doctors nowadays. So that's why we made a patient specific implants here. And this okay, this one they are taking the normal plate, the plate they are bending according to the patient dimensions. But when we are even nowadays with using the 3D printing, they are bending, but okay, after bending also they are not getting proper shapes. So that's why now in this case we are going to design and manufacture a patient specific implant. Okay, and now we are taking this CAD model. This CAD model we are mirrored from this region to this region, and we are extracted, we are removed with using the Boolean operation. Now okay, this is the region, this region we are going to place here. Then he got the symmetry, then the orbital balls will become up. So then the orbital balls are having a linear alignment. So okay, that's okay. For that purpose, we have to place this implant inside of this orbital floor. And now this CAD model we are prepared. Based on the CAD model, we are prepared a implant here. This is a final implant. This implant we are going to place inside of the patient here. Now you can, this is very small and it is having nearly 3-4 mm thickness only. Okay, now this implant we are manufactured here. Okay, this is this maxillum also manufactured with using the additive manufacturing technique. Okay, this manufactured with using the biocompatible material. And okay, we are tested, is it fitting properly or not on the 3D printed model, and we are tested with using the CAD model. Then okay, this implant is placed inside of the patient here. Now you can see here. Now this is before surgery, this is after surgery. Now you can see here. Now he's looking properly. Now he's getting his proper image. Okay, because of this patient specific implants. Okay, because of this because of these reasons, I can conclude, I can tell with using the 3D printing techniques, we can make a patient specific implants with using the CT images. Otherwise, we can't manufacture the patient specific implants. Still now we are tailored implants we are taking. Patient specific implants we can design and manufacturing with using the patient specific CT images and 3D printing technologies. Even okay, cosmetic surgery nowadays is very popular. Okay, we are designing one case. Okay, I'm going to show you within 2 minutes. Then I will conclude here. Okay, here there is uneven maxilla and mandible. Now he's looking and something is different. So that's why they are going to perform a cosmetic surgery to reconstruct the maxilla and mandible properly. Now in this case, okay, this is the leaf-4 fractures. When we are falling down, okay, here we are getting the fractures. Okay, these in the medical community, some leaf-4 fractures are already predefined. Leaf-4 fractures are there, and the region we can cut easily. And when we are falling, that at that region only, we are going to fracture. The bone will be going to fracture. So based on that leaf-4 fractures, we are going to perform a surgery. The doctors are going to perform a surgery, but where we have to perform the surgery, how much dimensions we have to move, because okay, now you can see here at this region, the teeth are this here, and at this region the teeth are here. From here to here, how much deviation is required to move, how much elongation is required from here to here, where you have to cut. All these things we are performed with using this 3D printing models here. Now here, we are going to perform the leaf-4 fracture here. That is, we are developed with using this CAD model. Then okay, we are moved from this to here. Okay, then the teeth are running properly. Now he can get the symmetric shape. But okay, how much elongation is required? How much deviation is required? Where to where deviation is required? All these things we are planned with using the CAD models, and we are prepared the template where we have to cut the leaf-4 fracture. Here we are going to cut the bone. But how we are going to fracture? For that, we are prepared the splint. This also we are designed with using this CAD modeling technique. And now we made a hollow portion. Here they are going to cut the region. Here at this region we are going to cut the leaf-4 fracture at this region here. Now how much elongation is required? That also we can do with using splint design. Okay, how much bone will be moved from this region to this region? How much elongation is required? Okay, that we can achieve with using this the splint design. Now you can see here. Like that we can design the models, we can manufacture the 3D printed model, and with using the 3D printing techniques, we can using this patient specific images, we can manufacture the implants. Here, this surgery performed in some private hospitals. That's why we are unable to show the patient images. And now we can from here we can say here, whatever the technologies we are giving to the doctors, that the doctors are ready to adopt the technologies that is given by Dr. B. Ravi Kumar. He's a professor in NIT Bombay. Okay, it is a true. I'm observing from 2017. Okay, after finishing my PhD, I performed so many various cases with use. Okay, I helped so many cases with using the 3D printing technologies. Okay, this is my conclusion. This is my topic. Sir? Hello, sir? Hello? Am I audible to you? Hello? Any query from the participants? Any questions from the participants? You can raise your question. Hello,
Hello.
Sir. Sir.
Yeah, am I audible to you?
Yeah, audible to you, sir.
Yeah,
Audible to me.
Yeah, so I would like to request all the participants, if they have any queries, they can continue. They
Okay,
can
sir.
ask.
Yeah, yes, sir. You can ask.
Any queries?
Yes. Hello.
Yes, sir.
Yeah, is it audible, sir?
Yeah, audible, sir. Audible.
Myself, S. Kupal from DAV Institute, Punjab.
Yes, sir.
I have queries related to this concept of 3D printing designing for the medical implants.
Yes, sir.
How do we get the CT scan data if we want to find some data? Is it available, readily available somewhere else in the online platform, or do we have to contact the doctors related with these things?
Actually, yes, sir. Actually, we can get the images from the radiologist.
Okay.
Suppose whatever the bone defect is there, okay, whatever the region is there, you have to collect the information from the radiologist. Okay, you have to take the dico images in form of the dico images. You have to collect that dico images. You can do processing, then you can develop the 3D printed models with using the dico images. You have to mention to the radiologist we require the dico images for the all the images.
Are they readily able to give it to us, or do we need to have some influence from some persons or the doctor's reference?
Yeah, some doctor references required, sir. Normally, they are not sharing openly the patient's data.
That is an issue over there.
Yeah, yes, sir. Yes, sir.
Okay, and one question is more. Do we need to adjust the fixture which you are fixing on the distractor manually?
Yeah, yes.
By the time schedule, we have to manually adjust that fixture.
Yes, sir. Yes, sir.
Okay, as the bone grows.
Yes.
Okay.
That is performed by the doctors. Just I made the distractor. I made the 3D printed models, but the surgery, all the things they are performed.
Certainly, that will be with the doctor there.
Yeah.
And one question more. Maybe you may be able to answer, may not be, because it is something related to the medical here. The nerve damages which may cause during the implantation.
Yes,
Can
sir.
you say something on this? Whether we are providing the nerve junctions over to the implants, or they are just dead then?
Sir, they are stitching the nerves also at the time of surgery. That facility is available nowadays.
They can be fixed onto the fixture, or sorry, the implant, or just onto the body parts, the natural body part.
The implant.
Yeah. So,
okay.
Is it able to?
Yeah.
Is it able to work with the implant also?
Yes, sir. Okay, nowadays, we are going to perform in vitro and in vivo tests also. Is it bone growing or not? All those things we have to perform the testing before implanting the patient. Without the certification, they are not going the surgery.
Because actually, I have in my mind that the implant is a dead object which we are implanting.
No. Actually, on the implant, the bone will be grow. Okay, that is I'm shown you already in my slide.
Yes.
So that is also required. Okay, here now you can see here. Even scaffolds, okay, that is very important factor to develop your scaffolds.
Yeah. And do we measure some kind of biting force before installing these implants? Because that is also one of the necessary point while installing the implants, the biting force.
Yes, sir. Okay, we have performed that strength analysis also. That is already I shown to you in my videos. Okay, we have performed this tensile test. All these things we have performed, and based on this strength, okay, we are going to.
That is basically the strength of your implant.
Yes, sir.
I'm talking of the object or the person whose implant is to be fitted in his body, whether he is able to take up that much of load for the implant.
Yeah, for the normal load, okay, 100 megapascal strength is there, sir. Okay, for the bone implant, we require the 100 megapascal strength.
Okay.
That is already that is defined in the medical community. That load.
Yeah, because the success rate of the implant will only depend upon the biting force which a person can have.
Yes.
Otherwise, it may not be sustainable.
Yeah. Okay, that's why you have to check is it withstanding 100 megapascal strength or not. Okay, that is your work. We have to define. We have to test.
Can you suggest some way for measurement of that biting force?
So that is very big study, sir.
Okay, no issue.
Yeah, you can communicate personally. I will tell you all this information, sir. Okay.
Right, sir. No issue.
Okay, sir.
Okay, sir. Thanks a lot, sir. Thanks a lot.
Okay, thank you, sir.
Sir, I have a doubt, sir.
Yeah, you can ask, sir.
Sir, if the medical implants are after some time they may disappear or continue with for a lifetime.
Medical implants are the continue in the lifelong. Only the scaffolds or the scaffolds only. Okay, it will be disappear. Okay, whatever the disappear implants are there, that is manufacturing by the biodegradable materials. Okay, we have to decide. Okay, is it prominent joints? Is okay? Which type of material is required? All those things you have to define before going to implanting, before going to planning the surgery.
Based on the implant place, we have to decide which material we have to take.
Which material is required. Like okay, based on that you have to use. Okay, biodegradable materials are available. Biocompatible material are also available in the medical industry.
Okay, sir. Biocompatible means it's a permanent one.
Biocompatible means permanent joint. Biodegradable means it will be decomposed automatically inside of the body.
Okay, sir. Thank you, sir. Thanks.
Sir, what is the difference between implant and scaffold?
Yeah, implant. Okay, here in the scaffold, the bone will be grow inside of the inside of the object. Okay, here in the to prepare scaffolds, we are preparing the porous structure. Under porous structure, the bone will be grow inside, and the scaffold will be decomposed automatically. That type of material we are using to prepare the scaffolds. But the bone is the permanent one, and okay, on that bone, the tissues will be growth. The implant is the
scaffold is biodegradable, but implant is not.
Not bio. That is the biocompatible, not biodegradable.
So it means it is bioresorbable, sir, or?
Yeah. Bioresorbable, biocompatible, both are same, sir.
Okay.
Biodegradable means it will be decomposed inside automatically.
Okay. Thank you.
Okay, sir.
Any other? One more doubt, sir.
Yeah.
Sir, in some parts of the bones, there is a bone marrow is present, sir.
Yeah.
If we are going to replace that type of bone, how we are going to manage with that bone marrow?
Normally, for the implant, we that is not suggestible the bone marrow, because suppose when we are manufacturing the metal implants, some metal powders are there inside. Maybe the powders after implanting the powders will be go inside of the blood. That is harmful to the patient. So that's why the doctors are not suggesting this type of hollow portions inside of the implant.
Okay, sir. Thank you, sir.
Okay, sir.
Any more questions from the participants? Any further question? Okay, I think they have done all the questions. Dr. M. Cherry, sir, thank you very much for your wonderful or informative session. People or participants enjoyed, and even I also enjoyed a lot your session.
Okay, sir.
Yeah. So
thank you, sir.
Yeah, thank you very much, sir.
Yeah,
and
thank you, sir. I'm also thanking you too for inviting as a guest speaker in your FDP. Thank you, sir.
Thank you, sir.
Thank you.
So the participants who are present here, I am sending one you can say a link, feedback link. Till today, whatever sessions happened regarding that, you have to fill this feedback link. I'm just going to put it in the chat box. So in that particular part, you have to fill all the details regarding whatever the session happened and whatever you understand about your understanding, about your basically about what did you understand. I'm just making it very important part to submit in the ATAL FDP. So I kindly request you all fill it and submit it on or before 5 p.m. Thank you very much. And tomorrow we will meet at 9:30 a.m. And tomorrow is the last date also of our ATAL FDP program. Thank you very much for your valuable presence and your patience. Thank you.